The planet closest to the Sun. There is a world that almost nobody thinks about. Not because it is small, though it is, the smallest planet in the solar system. Not because it is distant, though in certain respects it is among the most difficult worlds in the inner solar system to reach, but because it occupies a strange psychological position in the way most people think about the planets. It is neither the largest nor the most colorful nor the most dramatically ringed. It does not have the romantic associations of Mars or the mythological grandeur of Jupiter or the eerie beauty of Saturn seen through a small telescope on a clear night. It is simply the first one, the closest to the Sun, the innermost world, the planet that races around our star faster than any other, completing its orbit in just 88 Earth days, moving so quickly that ancient astronomers who tracked it across the sky must have found it almost maddening in its speed. Mercury, named for the messenger god of Roman mythology, the deity of speed of travel, of the swift crossing of distances. The name was chosen because this planet moves faster across the sky than any other visible to the naked eye, appearing and disappearing near the horizon with a fleetness that made it difficult to observe and easy to lose. And that difficulty, that elusiveness, has defined our relationship with Mercury ever since. Mercury has been known since antiquity. The ancient Assyrians recorded observations of it as early as the 14th century BCE. The Babylonians tracked its motion with sufficient precision to develop predictive tables. The ancient Greeks, observing it at different times, initially believed they were seeing two separate objects, one appearing in the evening sky after sunset, another appearing in the morning sky before sunrise, and named them separately before eventually recognizing they were the same planet following the same orbit on opposite sides of the Sun. This confusion is understandable. Mercury is never far from the Sun in the sky, never more than about 28 degrees away, which means it is only ever visible for a brief window after sunset or before sunrise, always low on the horizon, always competing with the lingering glow of twilight for the observer's attention. It never rises high into the dark sky, where telescopic observation would be comfortable and unobstructed. Every view of Mercury from Earth's surface is a view through the thick, turbulent, distorting air near the horizon, the worst possible conditions for clear observation. For much of human history, Mercury was the least well-observed of the 5 planets visible to the naked eye. Even in the telescope era, even with instruments far more powerful than anything available to Galileo, astronomers struggled to make out surface features clearly. The planet was too small, too close to the Sun, too low in the sky whenever it was visible. It kept its secrets for a long time. Let us establish the basic facts, because they are striking in themselves. Mercury is the smallest of the 8 planets. Its diameter is approximately 4,879 kilometers, making it only marginally larger than Earth's moon. If you placed Mercury and the moon side by side, they would look remarkably similar in size, though Mercury is substantially denser. It is smaller than 2 of the moons in the outer solar system, Ganymede, which orbits Jupiter, and Titan, which orbits Saturn, a fact that serves as a useful reminder of how arbitrary the category of planet can feel when confronted with the actual diversity of objects in the solar system. Its orbit takes it as close as 46 million kilometers to the Sun at perihelion, the closest point of its elliptical path, and as far as 70 million kilometers at aphelion. Earth's average distance from the Sun, for comparison, is 150 million kilometers. Mercury, at its closest, is less than a third of that distance. The Sun, seen from Mercury's surface, appears roughly 2.5 to 3.5 times larger in angular diameter than it appears from Earth, not a point of distant warmth, but an overwhelming presence dominating the sky, enormous and blazing and impossible to ignore. And yet, here is the first of Mercury's many surprises, and one that stops almost everyone when they first encounter it. Mercury is not the hottest planet in the solar system. This seems wrong. It should not be possible. Mercury is the closest planet to the Sun, closer by a considerable margin than any other world in the solar system. The intensity of solar radiation at Mercury's surface is between 4.5 and 10 times greater than the intensity at Earth's surface, depending on where Mercury is in its elliptical orbit. The Sun blazes above Mercury's rocky surface with a ferocity that exceeds anything experienced anywhere else in the inner solar system. And yet Venus, which orbits second from the Sun, farther away than Mercury, receiving less solar radiation per square meter of surface, maintains an average surface temperature of approximately 465 degrees Celsius. Mercury's dayside surface, despite receiving far more direct solar energy, reaches only about 430 degrees Celsius at its hottest. Venus is hotter than Mercury. The reason is atmosphere, or rather, Mercury's complete lack of one. An atmosphere does more than provide air to breathe. It traps heat, it distributes heat, it creates a greenhouse effect that keeps a planet's surface warmer than it would otherwise be from solar radiation alone. Venus has the most extreme greenhouse atmosphere in the solar system, a thick blanket of carbon dioxide with crushing surface pressure nearly 90 times greater than Earth's atmospheric pressure at sea level, and that atmosphere traps solar heat so effectively that the surface temperature is higher than Mercury's despite Venus receiving less total solar energy. Mercury has essentially no atmosphere. What little gas exists at its surface is so tenuous, a few atoms of sodium, oxygen, hydrogen, helium, that scientists technically call it an exosphere rather than an atmosphere. There is not enough gas to trap heat, not enough to distribute warmth, not enough to moderate anything. The result is a world of extremes that no genuine atmosphere could produce. A dayside scorching at 430 degrees Celsius and a nightside plunging to approximately minus 180 degrees Celsius, a temperature swing of over 600 degrees between day and night on the same planet. No other world in the solar system experiences a thermal range of that magnitude. Mercury's orbit is not only the fastest in the solar system, it is the most elliptical of any planet, the most stretched, the most oval-shaped, departing most significantly from the circular orbit that a planet in a perfectly stable gravitational environment would follow. This high eccentricity means that Mercury's distance from the Sun varies considerably between perihelion and aphelion, and that the intensity of solar radiation striking its surface changes substantially over the course of each orbit. The high eccentricity also played an important role in one of the most famous confirmations of Einstein's general theory of relativity. The orbit of Mercury precesses, the ellipse itself rotates slowly around the Sun over time, so that the point of closest approach shifts gradually from one orbit to the next. This precession had been known since the 19th century, but classical Newtonian mechanics could not fully account for its observed rate. There was a small but persistent discrepancy, approximately 43 arcseconds per century, that no adjustment to known parameters could explain. When Einstein published his general theory of relativity in 1915, one of the first things he calculated was the predicted precession of Mercury's orbit under the new theory. It matched the observed discrepancy exactly. Mercury, the small and overlooked innermost planet, provided one of the earliest and most precise confirmations that Einstein had fundamentally rewritten our understanding of gravity, space, and time. There is something worth pausing on here at the beginning of our journey with Mercury. This planet has been visible to the naked eye for the entirety of human history. Every civilization that ever developed astronomical knowledge was aware of it. It was named and tracked and incorporated into mythological systems and agricultural calendars and astrological traditions across dozens of independent cultures spanning thousands of years. And for almost all of that time, we knew almost nothing about it. We knew how fast it moved. We knew approximately where it would appear in the sky. We knew eventually how large it was and how far it orbited from the Sun. But its surface, its geology, its temperature extremes, its internal structure, the extraordinary secrets locked inside that small, dense, fast-moving world remained entirely unknown until the space age. The first spacecraft to visit Mercury arrived in 1974. Before that year, no human being had ever seen the surface of the closest planet to the Sun. A world visible every clear morning and evening for thousands of years of human history, and we did not know what it looked like until the 1970s. What that first spacecraft found, and what subsequent missions have continued to reveal, is a world stranger, denser, more geologically complex, and more scientifically surprising than almost anyone anticipated. But to understand Mercury as it is today, we must first understand Mercury as it was in the beginning. In the chaos of the early solar system, when the conditions that made this particular planet so unusual were being written into its very structure by forces of extraordinary violence. The story of Mercury begins not with the planet as we know it, but with the fire and collision of a solar system still finding its shape. Rest in that thought, the small, fast, misunderstood world racing around the sun, keeping its secrets for billions of years. The story of how it came to be is stranger than you might expect. Born in the early solar system. Every planet in the solar system began the same way. Not with drama, not with a single defining moment of creation, but with patience, the slow, almost incomprehensibly gradual accumulation of small things into larger things, driven by the most fundamental force in the universe, the force that shapes galaxies and builds stars and pulls scattered dust across the void of space into spheres dense enough to generate their own gravity. Everything began with a cloud. We have traveled this territory before, in our documentaries about Earth and the Moon, the vast rotating nebula of gas and dust that collapsed under its own gravity approximately 4.6 billion years ago, the ignition of the Sun at the center of the contracting disk, the protoplanetary disk of remaining material spreading outward and beginning the long process of assembling itself into planets. But here in the story of Mercury, the details of that process matter in a specific and important way, because Mercury did not simply form in the inner solar system. It formed in the most extreme region of the inner solar system, the region closest to the young sun, where temperatures were highest, where the solar wind was most intense, where the conditions for planetary formation were most demanding and most selective. And those conditions produced something unusual, something that planetary scientists are still working to fully understand. In the earliest phase of the solar system's formation, the protoplanetary disk was not uniform. Temperature varied dramatically with distance from the young sun. Close to the sun, in the region where Mercury now orbits, temperatures were so high that only the most refractory materials could survive in solid form. Refractory materials are those with the highest melting and boiling points, metals like iron and nickel, and certain silicate minerals with high melting temperatures. Volatile materials, water ice, carbon compounds, lighter silicates, simply could not condense into solid particles at those temperatures. The heat of the young sun vaporized them before they could accumulate. This means that the building blocks available for planet formation in Mercury's region of the disk were fundamentally different from the building blocks available farther out. In the asteroid belt, in the region of the outer planets, volatile-rich materials could condense and contribute to planetary growth. At Mercury's distance, only the dense, refractory, metal-rich materials were available in solid form. The result was a planet built from unusually dense raw materials, rich in iron and other metals from the very beginning of its formation. Before any geological processing occurred, before any internal differentiation separated lighter and heavier materials, Mercury was already metal-rich simply because the region where it formed was too hot to offer anything else. This is the first part of the explanation for Mercury's most striking characteristic, but it is only the first part. As Mercury grew from the dust and pebbles of the inner protoplanetary disk, the process of differentiation began, the same gravitational sorting that shaped every other rocky planet, with iron and nickel sinking toward the center to form a core, while lighter silicate rock rose toward the surface to form the mantle and crust. The result of this differentiation in Mercury's case was remarkable. Mercury's core is enormous relative to the planet's total size. While Earth's core makes up approximately 17% of the planet's total volume, Mercury's core makes up approximately 55 to 60%. More than half of Mercury, by volume, is core. By mass, the core represents approximately 70 to 80% of the planet's total mass. No other planet in the solar system has a core so dominant relative to its total size. Mercury is, in the most literal structural sense, mostly core, a vast ball of iron and nickel wrapped in a relatively thin shell of silicate rock. The mantle that lies between the core and the crust is thin by planetary standards. The crust itself is thinner still. If you could somehow remove Mercury's outer silicate layers and see only its core floating in space, you would be looking at an object roughly the size of the Moon, a sphere of dense iron and nickel nearly as large as our own natural satellite, wrapped in rock that adds relatively little to its total dimensions. Mercury is essentially a planetary core with a thin rocky coating. But the formation conditions of the inner solar system disk, however metal-rich they may have been, are not sufficient on their own to fully explain just how extreme Mercury's core fraction is. Even accounting for the refractory-rich building blocks available in that region, models of planetary formation suggest that Mercury should have a somewhat larger silicate mantle than it actually does. Something else happened, something that removed a significant portion of the silicate material that should, by the ordinary physics of planetary accretion, still be present today. The leading hypothesis involves a collision. Not the gentle, gradual accumulation of small bodies that constitutes the primary accretion process. Something more violent, a giant impact, similar in concept to the Theia impact that created Earth's moon, though different in its specific dynamics and outcome, that struck Mercury in its early history and stripped away a substantial fraction of its original mantle. In this scenario, early Mercury was a larger planet, perhaps significantly larger than it is today, with a more typical ratio of core to mantle. A large impacting body, perhaps comparable in size to a significant fraction of Mercury itself, struck at an angle and speed that preferentially ejected silicate material from Mercury's mantle into space, while leaving the dense iron core largely intact. The ejected silicate debris did not form a moon, as the material ejected from the Earth-Theia collision did. Mercury is so close to the Sun that the tidal forces from our star would have rapidly disrupted any moon-forming debris disk, preventing it from coalescing into a stable satellite. The ejected material was instead swept away, absorbed by the Sun, scattered into other orbits, perhaps contributing to the population of rocky bodies in the inner solar system. What remained after the impact was a Mercury stripped of much of its original mantle, smaller, denser, more core-dominated than it had been before. There is a second hypothesis that has gained traction in recent years, and it is in some ways even more dramatic than the giant impact scenario. It involves the Sun itself. In the early solar system, the young Sun went through a period of intense activity, radiating far more strongly in the ultraviolet and X-ray portions of the spectrum than it does today, and driving a powerful solar wind of charged particles outward through the inner solar system. In this hypothesis, this intense early solar radiation and wind were sufficient to vaporize and erode the outermost layers of the closest planetary body, Mercury, in a process called photoevaporation or impact erosion, gradually ablating the lighter silicate components from the planet's surface and upper mantle, while leaving the denser metallic core largely unaffected. Both hypotheses, the giant impact and the early solar erosion, may be partially correct. Some combination of formation in a metal-rich region of the disk, early giant impact stripping of the mantle, and solar erosion of volatiles and lighter silicates may together account for Mercury's extraordinary core fraction. The truth, as is often the case in planetary science, is probably more complex than any single elegant explanation. The ancient Mercury that emerged from these processes, whether shaped primarily by impact, by solar erosion, or by both, was a geologically active world. Its large iron core was hot, freshly differentiated, still generating substantial internal heat through radioactive decay and the residual energy of formation. Its mantle, thin as it was warm enough to drive volcanic activity. Its surface in those early hundreds of millions of years was shaped by both the internal heat pushing material upward through the thin crust and the relentless bombardment from outside, the same rain of asteroids and comets that struck every body in the inner solar system during the late heavy bombardment period. The result was a surface being simultaneously built from below and hammered from above, volcanic plains forming and being immediately disrupted by impacts, impact craters forming and being flooded by subsequent lava flows, a geological record being written and partially erased and rewritten in a continuous cycle of violence and construction. Some of that early record survives. The surface of Mercury today, heavily cratered, marked by enormous ancient impact basins, cut by long scarps and ridges that speak of a planet that has been slowly shrinking for billions of years, is the fossilized record of those first hundreds of millions of years. A geological archive, written in ancient rock, of the processes that shaped the innermost planet during the most violent era of solar system history. There is something quietly humbling about the scale of what we are describing. Mercury formed 4.6 billion years ago from the most extreme region of the early solar system's disk. It was shaped by heat so intense that most volatile materials simply could not survive. It was possibly struck by a body large enough to strip away a significant fraction of its mantle. It was eroded by a young sun far more active and intense than the sun we know today, and it emerged from all of this as the small, dense, fast-moving, core-dominated world that first spacecraft finally visited in 1974. All of that history, all of those billions of years of formation and collision and erosion, is preserved in Mercury's structure and written on its surface. And on that surface, the record of what came next is even more dramatic. The solar system's most ancient and most violent episode of planetary bombardment left its mark on Mercury more completely than almost anywhere else in the inner solar system, and nowhere is that record more spectacular than in the enormous scar that dominates one entire hemisphere of the planet. A scar so large that the shockwave from the impact that created it traveled entirely around the planet and converged on the opposite side, leaving a second geological signature thousands of kilometers away from the original impact site. That story belongs to what the surface of Mercury reveals, and it is waiting for us next. Rest in the ancient violence of those first billions of years, the fire, the collision, the slow settling of a world finding its final form. Mercury's surface remembers everything. A world of endless craters. Imagine a surface that remembers everything. Not selectively, not only the largest events or the most recent ones. Everything, every collision, every impact, every piece of debris that has struck it across 4 billion years of solar system history, preserved with a fidelity that no surface on Earth can approach, recorded in rock that has not been touched by rain or wind or the slow rewriting of plate tectonics. On Earth, the geological record is fragmentary. Erosion wears down impact craters within millions of years. Plate tectonics subducts old crust back into the mantle and replaces it with new material. Vegetation covers and stabilizes surfaces that would otherwise be shaped by wind. Water dissolves and deposits and transports. The oldest landscapes on Earth are only a few billion years old, and even they have been so thoroughly modified by subsequent processes that they bear little resemblance to their original form. Mercury has none of these erasure mechanisms. No rain, no rivers, no plate tectonics, no vegetation, no significant atmosphere to speak of. The surface that formed 4 billion years ago is in most regions, essentially the surface that exists today modified by subsequent impacts and a period of ancient volcanism, but not erased, not recycled, not significantly altered by any of the forces that continuously rewrite the faces of geologically active worlds. Mercury's surface is a document, and it is written in craters. The story of how that document came to be written begins with one of the most dramatic episodes in the history of the solar system, a period that planetary scientists call the Late Heavy Bombardment. Approximately 4.1 to 3.8 billion years ago, the inner solar system experienced an intense spike in the rate of asteroid and comet impacts. The evidence for this event is written on the Moon, whose heavily cratered highlands record a period of intense bombardment that produced the ancient, battered landscape visible to the naked eye tonight, and it is written, even more dramatically, on Mercury. The cause of the late heavy bombardment is believed to be related to a gravitational reshuffling of the giant outer planets. Jupiter and Saturn in the early solar system were not in their current orbital positions. Gravitational interactions between these enormous planets caused them to migrate, moving inward or outward through the solar system, their gravitational influence reshaping the orbits of countless smaller bodies as they went. This migration sent enormous numbers of asteroids and comets plunging into the inner solar system, subjecting the rocky planets to a rain of impactors far more intense than anything that has occurred since. For Mercury already close to the Sun, and therefore in the path of any object falling inward through the solar system, the late heavy bombardment was particularly severe. The entire surface was hammered, craters formed on top of craters. The oldest basins were modified by subsequent impacts before they had time to be flooded by volcanic material. The surface accumulated a deep layer of shattered and pulverized rock, the same kind of fine, powdery regolith we know from the Moon, ground down by billions of years of impact, gardening into a blanket of debris that covers the ancient crust. When the Mariner 10 spacecraft first imaged Mercury in 1974, scientists looking at the return photographs initially described the surface as looking almost identical to the Moon, heavily cratered, densely packed with overlapping impact features, ancient and battered. The resemblance is real. Both worlds experienced the same bombardment history. Both lack the erasure mechanisms that clean up planetary surfaces, and both preserve their ancient records in exposed rock. But Mercury's craters, examined more closely, tell a story that diverges from the Moon's in important ways. And the most dramatic of those divergences is written in the largest scar on Mercury's surface. The Caloris Basin is one of the largest impact craters in the solar system. It stretches approximately 1,550 kilometers in diameter, wide enough to contain the entire state of Texas with room to spare on all sides. Wide enough that if you stood at its center and looked toward the rim, the curvature of Mercury would hide the rim entirely below the horizon. Wide enough that, from directly above, it dominates an entire hemisphere of the planet. It was created by the impact of an asteroid or comet that planetary scientists estimate was approximately 100 kilometers in diameter, a body the size of a small mountain, traveling at tens of kilometers per second when it struck Mercury's surface. The energy released by that impact is almost impossible to meaningfully convey in human terms. It exceeded, by many orders of magnitude, the total energy released by all nuclear weapons ever built. It was one of the most energetic single events to occur on any rocky body in the inner solar system since the late heavy bombardment. The impact excavated a basin hundreds of kilometers deep in the first moments, before the surrounding rock rebounded, as rock does, behaving like a viscous fluid under extreme pressure, and partially filled the basin back in. The outer rings of mountains visible around the Caloris Basin today, concentric ridges rising kilometers above the surrounding terrain, are the frozen waves of that rebound rock that flowed outward from the impact site and solidified in the form it took as the energy dissipated. Volcanic material subsequently flooded the interior of the basin, creating the relatively smooth plains visible at its center, similar to the way lunar maria were created when ancient volcanic eruptions flooded the floors of large impact basins on the Moon. But the Caloris impact left a mark beyond the basin itself, a mark on the opposite side of the planet entirely. When an object strikes a planetary body with sufficient energy, the shockwave from the impact does not simply radiate outward from the impact site across the surface. It also travels through the interior of the planet, compressing and expanding the rock as it propagates, eventually converging on the point diametrically opposite the impact site on the far side of the world. At Mercury's antipode to the Caloris Basin, the point on the surface exactly 180 degrees away from the center of the impact, geologists have identified a region of extraordinarily chaotic terrain. Hills and ridges and valleys arranged in a jumbled, disrupted pattern unlike anything elsewhere on Mercury's surface. The terrain looks as if the surface was shaken violently from below, which is precisely what happened. The seismic energy from the Caloris impact traveled through Mercury's interior and converged at the antipodal point, disrupting the surface from beneath with sufficient force to create a geological feature visible from space. This antipodal terrain, called the chaotic terrain or weird terrain by planetary scientists, is a direct record of the shockwave from an impact that occurred on the opposite hemisphere. The energy of the Caloris collision was so enormous that it left its signature not just at the impact site, but on the far side of the planet, kilometers of rock disrupted by seismic energy that had traveled through the entire interior of Mercury to reach it. Two geological features, separated by the full diameter of the planet, written by the same event. Beyond the Caloris Basin, Mercury's surface is covered in craters ranging in size from kilometers to hundreds of kilometers in diameter. Planetary scientists have cataloged thousands of them, each one a record of a specific impact event, each one providing information about the size and velocity and angle of approach of the object that created it. The distribution of craters across Mercury's surface is not uniform. The heavily cratered highlands, regions where the ancient crust has survived largely intact since the late heavy bombardment, are saturated with craters, impact features overlapping and cutting through each other in a visual record of sustained, intense bombardment. The smoother volcanic plains, regions where ancient lava flows resurfaced the terrain after the worst of the bombardment had passed, have fewer craters, because they record only the impacts that have occurred since the volcanic flooding smoothed them. By counting the density of craters on different surfaces and comparing it to models of the impact rate over solar system history, scientists can estimate the ages of different regions of Mercury's surface. The heavily cratered highlands are the oldest, dating to the period of the late heavy bombardment, more than 3.8 billion years ago. The volcanic plains are younger, though still ancient by any human measure, perhaps 3.5 to 3.7 billion years old. Even the youngest surfaces on Mercury are older than the oldest surfaces on Earth. There is a particular quality to Mercury's cratered landscape that emerges from the images returned by the Messenger spacecraft, the NASA mission that orbited Mercury between 2011 and 2015 and returned more than 100,000 photographs of the planet's surface. It is a quality of stillness. The craters on Mercury do not erode. They do not fill with sediment or grow over with vegetation or get carved by rivers. They simply sit exactly as the impacts that formed them left them, their rims sharp, their floors flat or hummocky depending on their age and subsequent volcanic flooding, their ray systems of ejected material still visible in some cases as bright streaks radiating outward from the impact point. Some of those rays are fresh enough, in geological terms, that they appear as bright, unweathered streaks of excavated material. Fresh, in this context, means perhaps a billion years old, ancient by any terrestrial standard, but geologically young on a world where change is measured in timescales that dwarf the entire history of Earth's biosphere. The surface of Mercury is a museum, an open-air archive of solar system history, preserved by the very conditions that make the planet so inhospitable, the absence of the atmosphere and water and geological activity that elsewhere erase the evidence of what has come before. Every crater is a date, every basin is a chapter, every ray of ejected material is a sentence in a document that has been sitting on the surface of the innermost planet, untouched and unchanged, waiting for something capable of reading it. We are only just learning to rate it. Let the stillness of that ancient surface settle around you. The craters wait in the silence of the innermost planet, patient and perfectly preserved, and beneath that scarred surface, something extraordinary is happening that makes Mercury unlike any other world. The planet of extreme temperatures. Stand still for a moment and feel the temperature of the air around you. Whatever it is, whether you are warm beneath blankets on a cool night, or comfortable in a room kept at a steady temperature, or somewhere in the mild range that human bodies find tolerable without effort, the temperature you are experiencing right now falls within an extraordinarily narrow band of what is physically possible on the surface of a world. Absolute zero, the coldest temperature that physics permits, the point at which atoms have the minimum possible thermal energy, is minus 273.15 degrees Celsius. The surface of the Sun is approximately 5,500 degrees Celsius. The range between those two extremes spans nearly 5,800 degrees. And you in your room, on your planet, are somewhere in a sliver of that range so narrow, perhaps 50 degrees wide in terms of what humans can actually survive, that from the perspective of the full thermodynamic range of the universe, you occupy essentially a single point. Earth's atmosphere, as we have explored, is largely responsible for keeping you within that point. It moderates, it distributes heat, it prevents the day side from scorching and the night side from freezing. It wraps the planet in a thermal blanket that keeps the surface within the range where liquid water exists and biological chemistry functions. Mercury has no such blanket, and the consequences of that absence are written across its surface in temperature extremes that represent some of the most dramatic thermal conditions on any rocky body in the inner solar system. Let us begin with the heat. At perihelion, when Mercury is at its closest point to the Sun, approximately 46 million kilometers away, the intensity of solar radiation striking Mercury's sunlit surface is approximately 10 times greater than the intensity of sunlight striking Earth's surface. At aphelion, when Mercury is at its farthest point of approximately 70 million kilometers, the intensity is still approximately 4.5 times greater than Earth's. This radiation strikes a surface with no atmosphere to absorb or scatter it before it arrives, no clouds to reflect a fraction of it back into space, no air to distribute the heat laterally across the surface, just unfiltered, unmediated solar radiation striking dark rock directly, and rock is an efficient absorber of solar energy. The result at the subsolar point, the region of Mercury's surface directly beneath the Sun, where sunlight strikes at exactly perpendicular, is a surface temperature of approximately 430 degrees Celsius, not merely hot in any ordinary sense. Hot enough to melt lead, which liquefies at 327 degrees Celsius. Hot enough to melt zinc, which melts at 419 degrees Celsius. Hot enough that tin, aluminum, and several other metals would flow as liquids on Mercury's sunlit surface. The rocks themselves do not melt. Silicate minerals have melting points well above 430 degrees, but they absorb and radiate this heat in a way that makes the immediate environment above Mercury's dayside surface genuinely extreme. But the dayside heat, as extraordinary as it is, tells only half the story. Because Mercury rotates so slowly, completing one full rotation on its axis in approximately 59 Earth days, the day and night sides of the planet are exposed to their respective thermal conditions for very long periods. The day side bakes under the sun for weeks of Earth time. The night side sits in complete darkness, with no atmosphere to retain any of the heat generated during the long day for an equally extended period. In the absence of any atmospheric heat retention, the night side of Mercury radiates its thermal energy directly into the cold of space. And space is cold. Background temperature of the universe is approximately minus 270 degrees Celsius, just barely above absolute zero. With nothing to slow the loss of heat from the surface, Mercury's night side cools to approximately minus 180 degrees Celsius. The total temperature swing between the hottest point on Mercury's day side and the coldest point on its night side is therefore approximately 610 degrees Celsius. 610 degrees of temperature difference between the sunlit and shadowed surfaces of the same small planet. No other planet in the solar system experiences a thermal range of that magnitude. Not Mars, whose thin atmosphere provides some thermal moderation. Not the Moon, which is geologically similar to Mercury in its lack of atmosphere, but receives far less solar radiation at Earth's distance from the Sun. Mercury holds the record for the most extreme temperature contrast of any rocky body in the inner solar system by a considerable margin. Now comes the question that stops almost everyone when they first think carefully about Mercury's thermal environment. If Mercury is so close to the Sun, if it receives so much more solar radiation than Venus, which orbits farther out, why is Venus hotter? We touched on this in our opening section, but it deserves a deeper examination here, because the answer reveals something fundamental about how planetary temperatures actually work. The surface temperature of a planet is not simply a function of how much solar radiation it receives. It is a function of the balance between incoming energy and outgoing energy, between what the planet absorbs and what it radiates back into space. Venus has an atmosphere so thick and so dominated by carbon dioxide, with surface pressure approximately 92 times greater than Earth's at sea level, that it creates the most extreme greenhouse effect in the solar system. Sunlight penetrates the Venusian atmosphere with some difficulty. Venus's thick clouds actually reflect about 70% of incoming sunlight back into space, meaning Venus absorbs less total solar energy than you might expect. But the solar energy that does get through cannot escape. The thick carbon dioxide atmosphere traps it with extraordinary efficiency, and the surface temperature rises until the outgoing thermal radiation is just sufficient to balance the absorbed incoming energy. That equilibrium temperature turns out to be approximately 465 degrees Celsius, higher than Mercury's maximum dayside temperature of 430 degrees, despite Venus receiving less than half the solar radiation per square meter that Mercury receives. Mercury, by contrast, absorbs solar energy freely. Its dark rocky surface absorbs a significant fraction of the radiation that strikes it, but it also radiates that energy back into space just as freely, with nothing to trap it. The equilibrium between absorption and emission is reached at 430 degrees on the day side, and the moment sunlight stops striking a region, as Mercury's slow rotation carries it into its long night, the temperature plunges with nothing to slow it. Venus is a planet that cannot lose its heat. Mercury is a planet that cannot keep it. Both extremes, in different ways, make surface conditions inhospitable to life as we know it. The thermal environment at Mercury's surface has another dimension that is less often discussed but scientifically significant. The temperature does not simply vary between day and night. It varies with latitude, with albedo, the reflectivity of different surface materials, with the presence or absence of shadows cast by crater walls, and with the depth below the surface. Just centimeters below Mercury's surface, the wild temperature swings of the surface environment are dramatically moderated. Rock and soil are poor conductors of heat, and the thermal wave from the surface takes considerable time to penetrate downward. A few meters below the surface, the temperature becomes essentially constant, averaging somewhere between the extreme highs of the day side and the extreme lows of the night side, settling into a value that reflects the long-term average energy input from the sun. This subsurface thermal moderation has practical significance for the question of whether any environment on Mercury could, even in principle, support simple chemical processes. The surface itself is thermally lethal by any biological standard, but the shallow subsurface is a different environment, more stable, more temperate, somewhat shielded from the radiation environment of the surface. Not hospitable, not anywhere close to what biology requires, but less extreme than the surface above. There is one more thermal phenomenon on Mercury that deserves attention before we move forward, because it connects the planet's temperature extremes to one of the most surprising discoveries made about this hostile world: the permanently shadowed craters near Mercury's poles. Mercury's axial tilt is extraordinarily small, only about 0.034 degrees, essentially zero. This means the sun, as seen from Mercury's poles, never rises more than a fraction of a degree above the horizon. And in the floors of deep craters near the poles, craters whose rims are high enough to permanently block the already barely risen sun, no sunlight has fallen for billions of years. In those permanently shadowed floors, the temperature does not swing between 430 and minus 180 degrees Celsius. It does not swing at all. It maintains a nearly constant temperature of approximately minus 170 to minus 200 degrees Celsius, cold enough and stable enough for a substance to survive there that seems completely incongruous with everything we have just described about Mercury's thermal environment. Ice. Water ice sitting in the floors of permanently shadowed craters on the closest planet to the Sun, in one of the hottest environments in the inner solar system, preserved by the same thermal physics that makes the rest of Mercury so extreme. The complete absence of atmospheric heat distribution that causes the day side to boil and the night side to freeze also ensures that the shadowed polar craters are never warmed. The contrast is almost paradoxical. A planet where lead melts in the sunlight also harbors water ice that has survived for potentially billions of years. The same thermal physics that produces Mercury's extreme temperature swings also creates the cold traps where that ice is preserved. It is a world of contradictions, written in temperature. Every extreme on Mercury, the blazing day side, the frozen night side, the cold polar shadows, is a consequence of the same fundamental absence. No atmosphere, no thermal blanket, no moderating layer of gas between the raw physics of solar radiation and the bare rock of the surface. Earth's comfortable temperatures are not a natural default. They are a gift of chemistry and geology and biological history, the accumulated result of 4 billion years of atmospheric evolution. Mercury shows us, in the most direct possible way, what a planet's surface looks like without that gift. It looks like a world of 600 degrees of difference between one face and the other. A world where the sun blazes overhead with a ferocity that melts metals, and where the darkness of the night is so complete and so cold that it approaches the temperature of deep space. It is, by any measure, one of the most thermally extreme environments in the solar system. And yet, beneath all of that thermal violence, something remarkable is happening inside Mercury, something that has no right to exist in a planet so small and so ancient and so apparently simple. Something that is still not fully understood. Let the temperature extremes fade into the stillness around you. The surface of Mercury burns and freezes in its long, slow day, but deep inside, something extraordinary is still turning. Mercury's giant iron heart. There is a rule of thumb in planetary science. Small planets cool quickly. It is not a complicated principle. It follows from basic geometry and thermodynamics. A smaller body has a higher surface area to volume ratio than a larger one, which means it radiates heat from its interior more efficiently relative to the amount of heat it contains. A small planet loses its internal heat faster than a large planet, the way a small stone pulled from a campfire cools faster than a large boulder. Given enough time, and the solar system has had 4.6 billion years, a small rocky planet should cool completely. Its interior should solidify. Its geological activity should cease. Its magnetic field, if it ever had one, should die. Mars, with roughly half the diameter of Earth, appears to have lost most of its internal geological activity billions of years ago. Its magnetic field, once present, as remnant magnetism in ancient Martian rocks confirms, vanished when its core cooled and solidified, ending the dynamo that generated it. The planet became geologically quiet, its interior essentially frozen, its surface thereafter shaped almost entirely by external forces rather than internal ones. Mercury is smaller than Mars. Mercury should, by this reasoning, be even more thoroughly cooled, even more geologically dead, even more thoroughly stripped of any internal activity. And yet Mercury has a magnetic field. Not a strong one, not the robust, planet-encircling field that Earth's active liquid iron core generates, but a genuine, measurable, internally generated magnetic field, detected by Mariner 10 in 1974, and confirmed and characterized in detail by MESSENGER between 2011 and 2015. A field with a structure, indicating that it is produced by the same mechanism as Earth's, the flow of electrically conductive liquid metal in an outer core surrounding a solid inner core. For Mercury to have this field, part of its core must still be liquid, still flowing, still generating electrical currents, still active after 4.6 billion years in a planet too small to have any right to that kind of persistent internal activity. This is the central puzzle of Mercury's interior, and understanding it requires looking carefully at what Mercury's core is actually made of, and why it has not yet done what physics says it should have done long ago. We established in our second section that Mercury's core is extraordinary in its scale, comprising approximately 55 to 60% of the planet's volume, and perhaps 70 to 80% of its mass. No other planet in the solar system has a core so dominant relative to its total size. Mercury is, structurally, more core than anything else. This enormous core is composed primarily of iron and nickel, the same materials that form the cores of the other terrestrial planets. Iron and nickel are dense, electrically conductive metals whose behavior under the extreme pressures and temperatures of a planetary interior has been extensively studied in laboratories and modeled in computer simulations. Pure iron at the pressures present in Mercury's core would solidify, become solid, at temperatures somewhat lower than those at which it remains liquid at Earth's surface. The question of whether Mercury's core has solidified, therefore, depends on whether the temperature of the core has cooled below the solidification point of its constituent materials. For a pure iron core of Mercury's size, the answer should be yes, it should have solidified long ago. The planet is too small to have retained enough heat to keep a pure iron core liquid for 4.6 billion years. But Mercury's core is almost certainly not pure iron. The key to understanding Mercury's persistent liquid outer core lies in the presence of lighter elements mixed into the iron and nickel. When planetary cores form through differentiation, the gravitational separation of dense metals from lighter silicates, they do not segregate perfectly. Some fraction of lighter elements is incorporated into the core alongside the iron and nickel. On Earth, the core contains significant amounts of lighter elements, sulfur, oxygen, silicon, carbon, hydrogen, whose identities and proportions are still debated, but whose presence is required to explain the observed density of the core, which is lower than pure iron would produce at those pressures. Lighter elements mixed into iron have a critical effect on its behavior. They lower the melting point, the temperature at which iron transitions from solid to liquid, through a process analogous to the way salt lowers the freezing point of water. A mixture of iron and sulfur, for example, melts at a significantly lower temperature than pure iron alone. A core containing substantial amounts of such light elements can therefore remain partially liquid at temperatures that would have solidified a pure iron core long ago. Mercury's core, current models suggest, contains a significant fraction of light elements, possibly sulfur, silicon, or other compounds, that have kept its melting point low enough for a liquid outer shell to persist despite the planet's small size and advanced age. The exact composition is not yet known with certainty, but the fact of the liquid outer core, required to explain the magnetic field, constrains what the composition must be. Mercury's core has stayed liquid, in defiance of simple expectations, because it is not simply iron. It is iron alloyed with something that keeps it from solidifying. The magnetic field that this liquid core generates is unlike any other in the solar system. Mercury's magnetic field is approximately 1 to 2% the strength of Earth's magnetic field, weak by any comparison. Too weak to create the kind of protective magnetosphere that shields Earth's atmosphere from the solar wind. Too weak to deflect cosmic radiation from Mercury's surface to any meaningful degree. Too weak to explain by the same dynamo mechanism that operates in Earth's much larger and more vigorously convecting liquid outer core. And it has another peculiarity that puzzled scientists from the moment MESSENGER began mapping it in detail. Mercury's magnetic field is not centered on the planet's geographic center. On Earth, the magnetic dipole, the north-south axis of the magnetic field, is approximately aligned with the planet's rotational axis and passes through its center. Small offsets exist, and the field wanders over geological time, but broadly it is centered on the planet. Mercury's magnetic field is offset significantly northward from the planet's center, by approximately 480 kilometers, nearly 20% of the planet's radius. The north magnetic pole is much closer to the planet's surface than the south magnetic pole. The field is asymmetric in a way that is both striking and currently unexplained. No current model of planetary magnetic field generation fully accounts for this offset. It may reflect asymmetries in the convection patterns within Mercury's liquid outer core. It may be related to the unusual composition of the core or the specific structure of the solid inner core beneath it. It may be telling us something fundamental about planetary dynamo mechanics that we do not yet fully understand. The offset field is one of Mercury's most actively discussed scientific mysteries, and MESSENGER's successor, the BP Colombo mission, currently en route to Mercury, carries instruments specifically designed to characterize the field in greater detail and provide new constraints on the models trying to explain it. Beneath the liquid outer core, Mercury almost certainly has a solid inner core. The evidence for this comes both from theoretical modeling of how a planetary core of Mercury's composition would evolve over 4.6 billion years, and from more direct seismic inference. When MESSENGER measured the planet's gravitational field and its response to the tidal forces from the Sun, the way Mercury's shape subtly distorts under solar gravity, the measurements constrained models of the interior in ways consistent with a solid inner core of substantial size, possibly comprising 40 to 50% of the total core radius. If confirmed, Mercury's solid inner core is proportionally very large, a significant fraction of an already enormous core. The planet's interior in cross-section would show a thin silicate crust, a relatively thin silicate mantle, a liquid iron-rich outer core, and a large solid iron inner core at the center. Layer upon layer of different material states, from the cold rigid crust at the surface to the blazing solid iron heart at the center. The pressure at Mercury's center, though far lower than the pressure at Earth's center, because Mercury is smaller and less massive, is still sufficient to affect the behavior of materials in ways that require careful experimental and theoretical work to understand. There is one more consequence of Mercury's enormous iron core that deserves attention, one written not in the planet's interior, but on its surface. Mercury is shrinking. As the planet's interior has cooled over billions of years, even the cooling that has occurred without complete solidification, the iron has contracted slightly. Cooling iron occupies less volume than hot iron, and as Mercury's vast core has slowly cooled, the planet's total volume has decreased. Not dramatically, not in any way that any observer could detect on human timescales, but cumulatively, over billions of years, the shrinkage has been sufficient to leave visible traces on the surface. Those traces appear as long, sinuous cliffs, called lobate scarps, that cut across Mercury's surface for hundreds of kilometers. These scarps formed when the contracting interior caused the crust to buckle and thrust upward along fault lines, one section of crust overriding another, as the total surface area available decreased with the shrinking planet beneath it. The scarps are Mercury's stretch marks, or rather its compression marks, the wrinkles that formed as the planet contracted around its slowly cooling iron heart. Some of these scarps are geologically young again in the planetary sense, perhaps a billion years old, but young enough to suggest that Mercury's contraction is ongoing, that the planet is still slowly shrinking, that the cooling and solidification of the interior is still in progress even now. Mercury is not a dead planet. It is a dying one slowly, on timescales that reduce any human perspective to insignificance, but actively cooling, actively contracting, its surface still responding to the slow changes happening deep inside. The giant iron heart is still cooling. In a universe that operates by consistent physical laws, where small planets cool faster than large ones, where ancient cores solidify, where geological activity is the privilege of large, heat-retaining worlds, Mercury is a reminder that the universe does not always follow simple expectations. A planet too small to have retained its geological activity, a core too large for its planet's size, a magnetic field too weak to protect and too persistent to ignore, a liquid interior that should have solidified long ago, but has not, kept fluid by chemistry subtle enough to have resisted simple characterization for decades of spacecraft exploration. Mercury's iron heart beats quietly and slowly, and against the expectations of simple planetary science. And inside that heart, the questions are only beginning. Rest in the deep interior of the smallest planet, the iron core still warm, still partly liquid, still slowly cooling in the dark. And in our next passage, we rise back to the surface and look up at a sky unlike any other in the solar system. The sun from Mercury. Close your eyes for a moment and picture the sun. The sun, you know, the one that rises every morning over the horizon of a familiar landscape, that climbs through a blue sky scattered with clouds, that sets in the evening in gradients of orange and gold and deep violet. The sun that warms the back of your hand on a clear afternoon, that you instinctively look away from when it catches your eye at the wrong angle, that seems from a lifetime of experience to be simply there. A fixed, reliable, comprehensible presence in the sky above the world you know. Now imagine standing on the surface of Mercury and looking up. Everything you have just pictured is gone. The blue sky is gone. There is no atmosphere to scatter light into color, no diffuse illumination to wrap the world in ambient glow. The sky is black, not the soft, star-scattered black of a clear night on Earth, but a hard, absolute black, the raw vacuum of space, directly overhead, visible in every direction except where the sunlit surface reflects light upward. And in that black sky, something is hanging that bears only a passing resemblance to the sun you know. From Mercury's surface at perihelion, when the planet is at its closest point to the sun, the solar disk appears approximately 2.5 to 3.5 times larger in angular diameter than it appears from Earth. But the visual difference is not simply one of size. The sun from Mercury is overwhelming in a way that no description fully captures. It does not look like a warm, friendly star. It does not look like the benevolent source of light and warmth that human cultures across history have worshipped and celebrated. It looks like what it actually is, a nuclear furnace of almost incomprehensible power, occupying a significant fraction of the sky, blazing with an intensity that has no analog in ordinary human experience. The light it casts on Mercury's surface is not the soft, scattered, atmospherically diffused light of an Earth afternoon. It is hard, direct, unmediated radiation, arriving without any atmosphere to filter it, striking rock and shadow in a contrast so extreme that the landscape seems almost to have been drawn in pure black and white. Sunlit surfaces blaze with an intensity 4.5 to 10 times greater than the most intense sunlight on Earth. Shadows are absolute, not the dim, light-filled shadows of an overcast day, or even the darker shadows of a clear desert afternoon, but shadow that is essentially the darkness of space, created by the complete absence of scattered light. To stand on Mercury's sunlit surface would be to exist in a world of blinding light and perfect darkness simultaneously, with no gradation between them. But the visual appearance of the sun from Mercury is not the most unusual feature of the sky. What is most unusual, what takes a moment of concentrated thought to fully appreciate, is the way the sun moves. Mercury's rotation, as we have noted, takes approximately 59 Earth days. Its orbit around the sun takes approximately 88 Earth days. And the relationship between these two numbers, the rotational period and the orbital period, produces a phenomenon in Mercury's sky that has no equivalent anywhere else in the solar system. Because Mercury rotates so slowly relative to how fast it orbits, the apparent motion of the sun across Mercury's sky is not the simple, predictable arc that any Earth observer takes for granted. The sun does not simply rise in one direction, arc across the sky, and set in the opposite direction at a roughly constant rate. Instead, the sun's motion, as seen from Mercury's surface, is driven by the combination of the planet's slow rotation and its orbital motion. And because those two motions operate on comparable timescales, and because Mercury's orbit is significantly elliptical, the result is something genuinely strange. Near perihelion, when Mercury is moving fastest in its orbit, sweeping around the Sun at its greatest orbital velocity, in accordance with Kepler's laws of planetary motion, the planet's orbital angular velocity briefly exceeds its rotational angular velocity. In plain language, Mercury is orbiting the Sun faster than it is spinning on its own axis. From the surface of Mercury, this creates something remarkable. Imagine watching the Sun from a particular location on Mercury as the planet approaches perihelion. The Sun has been rising slowly, far more slowly than the Sun rises on Earth, because Mercury's day is so much longer. It climbs above the horizon with the patience of a geological process, brightening and growing and filling more of the black sky as it ascends. And then near perihelion, the Sun stops. It pauses in the sky not metaphorically, not approximately, but actually stops its westward motion across the sky and reverses direction. It moves backward, eastward, for a period before the planet's rotation reasserts itself, and the Sun resumes its normal westward motion and continues across the sky. This reverse motion is brief by cosmic standards, but it produces a phenomenon that, from certain locations on Mercury's surface, is even more dramatic. From specific locations on Mercury, the longitudes where the Sun would ordinarily rise at perihelion, the Sun rises above the horizon, reverses and sets again briefly, then rises a second time and continues on its way across the sky. A double sunrise. The Sun rises, sets, rises again, all without any clouds or obstruction, purely as a consequence of the geometry of Mercury's orbit and rotation. And at the opposite end of the planet, where the Sun would ordinarily be setting at perihelion, the reverse happens. The Sun begins to set, rises briefly back above the horizon, then sets again. A double sunset. This phenomenon, remarkable enough as a geometric curiosity, has a name in the technical literature. It is sometimes called the Mercurian Sun reversal, or more colloquially, the retrograde solar motion, and it is a direct consequence of the same orbital resonance that defines Mercury's relationship with the Sun. Mercury rotates exactly 3 times for every 2 orbits around the Sun, a 3-2 spin-orbit resonance, similar in concept to the 1-1 resonance that keeps the Moon always showing the same face to Earth, but different in its specific ratio. This resonance was established early in Mercury's history by tidal interactions with the Sun, the same kind of gravitational braking that locked the Moon's rotation to its orbit around Earth, here acting on a planet close enough to the Sun for solar tidal forces to be significant on geological timescales. The 3-2 resonance means that a solar day on Mercury, the time from one sunrise to the next, is not 59 Earth days, but approximately 176 Earth days. 2 full Mercurian years pass in the time it takes for the Sun to complete one apparent circuit of Mercury's sky. The day is longer than 2 years. To be on Mercury for what would locally count as a single day would mean being there for 176 Earth days, during which time Mercury would complete 2 full orbits of the Sun, experiencing 2 perihelions and 2 aphelions, the Sun twice swelling and shrinking in apparent size as the distance to the Sun varied with the elliptical orbit. It is a timekeeping challenge of a kind that no human civilization has ever confronted. The Sun's apparent size variation over the course of a Mercurian day is itself striking. Because Mercury's orbit is so elliptical, more elliptical than that of any other planet, the distance to the Sun changes significantly between perihelion and aphelion. At perihelion, the Sun appears at its largest, approximately 3.5 times the angular diameter it presents to Earth. At aphelion, it shrinks to approximately 2.5 times Earth's apparent solar diameter. This means the Sun as seen from Mercury's surface is not merely larger than as seen from Earth. It is variably larger, pulsing slightly in apparent size over the course of the long Mercurian day as the planet traces its elliptical orbit. The same observer standing on the same spot on Mercury's surface would see the Sun grow and shrink in a cycle 88 Earth days long, repeating twice in every Mercurian solar day. The variation in solar radiation intensity accompanying this size change is not trivial. The difference in solar energy received at perihelion versus aphelion, roughly a factor of 2, is one of the drivers of the thermal extremes we explored in our last section. The surface temperature at the subsolar point shifts substantially over the Mercurian year, from its peak near perihelion to somewhat lower values near aphelion. Mercury's sky does not provide the consistent, predictable solar environment that Earth's sky does. It provides something more variable, more dramatic, and in its way more dynamic, a sky in which the dominant feature grows and shrinks and reverses direction, and the day lasts longer than 2 years. The blackness of that sky deserves one more moment of attention. On Earth, the atmosphere fills the sky with diffuse light during the day, and a blue color that many humans find instinctively beautiful and calming. Even at night, light pollution from human civilization brightens the sky over most populated areas. True darkness, the absolute darkness of a clear sky far from any artificial light source, is something relatively few people on Earth regularly experience. On Mercury, the sky is always that dark. During the day, with the sun blazing in the sky above, the rest of the sky is black. Stars are not visible in the dayside sky. The surface reflects too much light for the eye or any camera calibrated for dayside brightness to also detect the comparatively faint light of stars. But they are there in the blackness, unreachable by vision but real. Toward the horizon on the night side, or at the terminator, the boundary between the sunlit and shadowed hemisphere, stars would be visible in extraordinary numbers. No atmosphere to scatter their light, no moon to illuminate the sky, no light pollution. Just the stars, burning with a steadiness no earthly atmosphere could provide, in numbers that would be overwhelming to any human eye accustomed to even the darkest terrestrial sky. Mercury offers the most unmediated view of the universe of any rocky body in the inner solar system. The stars as they actually are, not softened by atmosphere, not washed out by moonlight, not obscured by weather. The raw cosmos, visible from the surface of the sun's closest companion. Let that black sky and blazing sun settle into stillness around you. The view from Mercury is unlike anything in human experience, and beneath that extraordinary sky, hidden in the coldest places on the closest planet to the sun, something waits that should not be there. Ice at the edge of hell. Some facts about the universe take a moment to fully arrive. You read the words or hear them, and there is a brief pause, a fraction of a second in which the information is present, but the meaning has not yet settled. And then it does, and something shifts, and the world seems slightly stranger and more interesting than it did a moment before. Here is one of those facts. The planet closest to the sun, the world that receives between 4.5 and 10 times more solar radiation per square meter than Earth, whose dayside surface is hot enough to melt lead, whose entire existence seems to be defined by heat and radiation, and the overwhelming presence of a star only 46 million kilometers away at its closest, contains water ice. Not a trace, not a molecule or two locked in a mineral lattice or implanted in the surface by the solar wind. Substantial deposits of water ice, sitting on or just below the surface, in locations that have not seen sunlight in billions of years, preserved in conditions cold enough to keep them frozen indefinitely, while the rest of the planet bakes under the most intense solar radiation in the inner solar system. Ice on Mercury. The fact lands strangely. It seems like a contradiction, a physical impossibility written in the same sentence as the planet whose name is synonymous with proximity to the sun. And yet the ice is there, confirmed by multiple spacecraft and multiple measurement techniques, one of the most surprising and consequential discoveries in the history of planetary science. To understand how ice survives on Mercury, you have to return to a concept we have visited before in our exploration of the Moon's polar regions, but which takes on an even more dramatic character when applied to the innermost planet. Mercury's axial tilt is essentially zero, not approximately zero, not nearly zero in the way that scientists sometimes use that phrase to mean a small but non-zero value. Mercury's axial tilt is 0.034 degrees, so close to zero that it is, for all practical purposes, nothing. The planet's rotational axis is very nearly perpendicular to the plane of its orbit around the Sun. The consequence of this near-zero tilt is that the Sun, as seen from Mercury's poles, never rises more than 0.034 degrees above the horizon. It does not arc across the sky. It does not climb high enough to illuminate the floors of deep craters. It simply skims along the horizon, present but horizontal, casting shadows of nearly infinite length across the terrain, its light grazing the tops of crater rims and ridges, while the crater floors below remain in permanent shadow. Certain craters near Mercury's poles are deep enough and their rims high enough that the floor of the crater is completely shielded from any direct solar radiation. Not just most of the time, not just during Mercury's night, always, permanently. For as long as Mercury has existed in its current configuration, billions of years, sunlight has not touched those crater floors. And in the absence of sunlight, something extraordinary becomes possible. The temperatures in Mercury's permanently shadowed craters are extraordinary in their own right, extraordinary in the opposite direction from the dayside heat. Without any sunlight to warm them, and with Mercury's lack of atmosphere preventing any lateral heat transport from warmer regions, these permanently shadowed crater floors reach temperatures of approximately -170 to -200 degrees Celsius. At those temperatures in a vacuum, water ice is extraordinarily stable. The vapor pressure of ice at -170 degrees is so low, so vanishingly small, that the rate at which water molecules escape from the ice surface is essentially zero on any timescale of practical relevance. The ice simply stays. It has nowhere to go and no energy to go there with. Locked in place by cold so extreme that the random thermal motion of water molecules is insufficient to overcome the attractive forces holding the ice crystal together, it sits in the shadow and waits with the patience of deep geological time. But where did it come from? The origin of Mercury's polar ice is thought to be similar to the origin of ice deposits on the Moon, delivery from outside, primarily by comets and water-bearing asteroids that have struck Mercury throughout its history. When a comet or hydrated asteroid strikes Mercury, the impact releases an enormous pulse of energy that vaporizes the projectile and a significant volume of surface rock. Some of the water from the impacting body is destroyed, dissociated by the energy of the impact, its hydrogen and oxygen atoms scattered into space by the solar wind. But some fraction of the water survives as vapor, dispersing across Mercury's surface in the tenuous exosphere. These water molecules then undergo a random walk across Mercury's surface, hopping from location to location as they are alternately vaporized by sunlight and refrozen when they land in shadow. Most of them eventually reach a sunlit region and are destroyed by ultraviolet radiation, their hydrogen atoms lost to space. But some fraction, through the statistics of random motion across a sphere with two very cold poles, finds its way to the permanently shadowed polar craters. And once a water molecule enters a permanently shadowed crater and settles onto the cold floor, it does not leave again. It is trapped, cold trapped in the technical language of planetary science, immobilized by temperatures so low that the activation energy needed to escape exceeds the thermal energy available. Over billions of years, impact after impact adding small contributions to the ice inventory, the deposits have built up, not all at once, not from a single dramatic event, but patiently, molecule by molecule, across the full history of the solar system. The first evidence for Mercury's polar ice came not from a spacecraft, but from a radar telescope on Earth. In 1991, scientists using the Arecibo Observatory in Puerto Rico, the largest radio telescope on Earth at the time, bounced radar pulses off Mercury's surface and analyzed the reflected signals. In the polar regions, they found something unexpected. The radar reflectivity of certain areas near Mercury's poles was anomalously high, far higher than the reflectivity of ordinary silicate rock. This kind of anomalously high radar reflectivity is characteristic of water ice. Ice is highly transparent to radar wavelengths. Radar waves penetrate the ice, bounce off deeper layers, and return to the receiver with a strength and coherence that rock surfaces do not produce. The same radar signature had been used to detect ice deposits on Mars and had been found in the permanently shadowed craters of the Moon. But Mercury was a surprise. Nobody had expected to find radar-bright material on the closest planet to the Sun. The result was greeted with interest, then skepticism, then cautious excitement as the implications were worked through. If the radar-bright material was ice, and the radar signature was consistent with ice, then water ice was present at the poles of Mercury, surviving in the permanently shadowed craters while the rest of the planet baked. The hypothesis needed confirmation. It got it, definitively, more than 2 decades later. The Messenger spacecraft, which entered Mercury orbit in March 2011, carried instruments specifically designed to address the polar ice question. A neutron spectrometer measured the flux of neutrons emitted from Mercury's surface by cosmic ray bombardment, the same technique used by the Lunar Prospector spacecraft to detect hydrogen at the Moon's poles. Hydrogen, the key component of water, slows neutrons in a characteristic way, and the messenger neutron spectrometer found exactly the signal expected from hydrogen-rich material concentrated in Mercury's polar regions. A laser altimeter measured the reflectivity of Mercury's surface at infrared wavelengths and found that the permanently shadowed regions near the poles were highly reflective, consistent with exposed ice surfaces in some areas, and in others with a thin layer of darker material overlying the ice. A thermal model confirmed that the regions where ice was detected were precisely the regions where temperatures were cold enough for ice to survive indefinitely, the permanently shadowed crater floors and their immediate surroundings, where sunlight had not fallen in billions of years. The convergence of evidence was unambiguous. Mercury has water ice at its poles. The Arecibo radar observation from 1991 had been correct. The messenger data revealed something additional that added another layer of complexity to Mercury's polar story. In some locations, the ice appeared to be covered by a thin, dark layer, a coating of material more absorptive than the ice itself, sitting on top of the ice deposits and partially insulating them from the warmer temperatures above. This dark material may be organic compounds, carbon-bearing molecules deposited alongside the water by the same cometary and asteroidal impacts that delivered the ice. Comets are rich not only in water ice but in organic molecules, the building blocks of complex carbon chemistry. If the same impacts that delivered water to Mercury's poles also delivered organic material, those organics could have been cold-trapped alongside the water, accumulating in the same permanently shadowed environments and eventually forming the dark coating observed by messenger. Organic material at Mercury's poles, sitting in craters that have not seen sunlight since they formed billions of years ago, preserved by the same cold that preserves the ice beneath them. It is not life. It is not the chemical precursors to life in any active sense. Mercury's environment is far too hostile, and the temperatures far too extreme everywhere outside the polar shadows for any chemistry approaching biology to operate. But the presence of both water ice and organic material in the same cold-trapped environments is a reminder that the chemistry of comets and asteroids, the same chemical inventory that may have contributed to the origin of life on Earth, reaches even the most extreme environments in the inner solar system. Mercury's polar ice deposits are not simply a scientific curiosity. They are a window into the chemistry of the early solar system, preserved in cold storage at the edge of the most intense heat in the inner planets. There is a poetry to this discovery that is difficult to ignore. The planet closest to the Sun, the world that seems, more than any other in the solar system, to be defined entirely by heat and radiation and the overwhelming proximity of a star, and at its poles, in shadows so deep and cold that they have maintained temperatures near -200 degrees Celsius for billions of years, water ice sits quietly waiting. The same water ice that fills Earth's oceans, the same water ice found in comets born in the cold outer reaches of the solar system, delivered here to the innermost planet by the long chain of impact events that have shaped the solar system since its formation, and kept here, frozen and stable, by the same thermal physics that makes Mercury's sunlit surface so lethally hot. The extreme heat and the preserved ice are not contradictions. They are two expressions of the same underlying reality, a planet with no atmosphere and no way to moderate its thermal environment, where the presence of sunlight means blazing heat and the permanent absence of sunlight means cold preserved across geological time. Mercury holds ice because Mercury has no atmosphere. The very condition that makes the planet so extreme is also the condition that makes the preservation of its polar ice possible. Let that paradox rest softly in your mind, ice at the edge of hell, patient and cold in the permanent shadow, while above the crater rim the sun blazes with a ferocity that melts metal. And in our next passage, we discover the extraordinary story of how we came to know all of this, the missions that changed Mercury forever. The missions that changed everything. For most of human history, Mercury was a point of light. Not even a particularly impressive point of light, not the brightest object in the night sky. That distinction belongs to Venus, which blazes so brilliantly that it is sometimes mistaken for an aircraft. Not the most dramatic, Jupiter, even to the naked eye, has a presence that commands attention. Mercury was simply a fast-moving, elusive, difficult-to-observe point of light near the horizon in the brief windows around sunrise and sunset, tracked by astronomers, incorporated into calendars and mythologies, but never truly seen. Telescopes improved the situation marginally. Through a telescope, Mercury resolved from a featureless point into a tiny disk, exhibiting phases, like the Moon and Venus, as different fractions of its sunlit hemisphere became visible from Earth at different points in its orbit. But the disk was small and always low on the horizon, and the atmospheric distortion that blurs any object observed near the horizon made detailed surface mapping essentially impossible. By the middle of the 20th century, as the space age began and humanity turned its first spacecraft toward the planets, Mercury remained among the least known bodies in the solar system. Its surface had never been clearly imaged. Its internal structure was unknown. Its temperature extremes had been roughly estimated but not measured. Its magnetic field had not been detected. The basic facts about the planet, the facts that any decent encyclopedia of the solar system should contain, were simply absent. What was known about Mercury in 1960 could be summarized in a few paragraphs. What we know today fills entire scientific journals. The transformation happened in 3 acts. The first act was Mariner 10. Mariner 10 was not originally designed solely to visit Mercury. Its mission was a tour of the inner solar system, a trajectory that would carry it past Venus first, using that planet's gravity to bend its path and send it on toward Mercury. This gravitational assist technique, using the gravity of one planet to redirect a spacecraft toward another, was relatively new in the early 1970s, and Mariner 10 was one of the first missions to use it operationally. The spacecraft launched on November 3, 1973. It passed Venus in February 1974, its instruments gathering data on the Venusian atmosphere and cloud structure before the planet's gravity bent its trajectory inward. And on March 29, 1974, Mariner 10 made its first flyby of Mercury, the first spacecraft from Earth to visit the innermost planet. What the cameras showed stopped scientists in their tracks. The surface of Mercury was cratered, heavily, densely, dramatically cratered looking, in the first images returned from that first flyby, almost indistinguishable from the Moon. Craters of all sizes, overlapping and cutting across each other, ancient basins and younger impacts, and the smooth plains of what appeared to be ancient volcanic flooding. The surface was old, profoundly, almost incomprehensibly old, a record of the solar system's early bombardment history, written in rock that had not been significantly modified since. But the craters were not the most surprising finding of Mariner 10's first encounter. That distinction belonged to the magnetic field. When Mariner 10's magnetometers detected a magnetic field at Mercury, a genuine, internally generated planetary magnetic field, weak but unmistakable, it was one of the most unexpected results in the history of planetary exploration. Mercury was too small, too slow rotating, too apparently simple to have an active dynamo generating a magnetic field. The detection forced an immediate revision of the theoretical understanding of how planetary magnetic fields are generated and what conditions are necessary to sustain them. A single flyby had overturned a fundamental assumption about planetary science. Mariner 10 flew past Mercury not once but 3 times, in March 1974, September 1974, and March 1975, before its maneuvering gas was exhausted and the mission ended. Each flyby returned new images and new data, but each flyby illuminated the same hemisphere of Mercury. Due to the resonance between Mercury's orbital period and the spacecraft's own orbit around the Sun, Mariner 10 always encountered Mercury with the same hemisphere facing the Sun, and therefore the same hemisphere facing the spacecraft's cameras. The result was that approximately 45% of Mercury's surface was imaged by Mariner 10. 45%. More than half of the planet, an entire hemisphere plus some, had never been seen by any spacecraft when Mariner 10's mission ended in 1975. A full hemisphere of the innermost planet remained completely unknown, as blank on planetary maps as the far side of the Moon before the space age, as unexplored as any territory in the solar system. Mercury returned to the category of the partially known, better understood than before, transformed in its scientific significance by the magnetic field discovery, mapped in almost half its extent, but still deeply, frustratingly incomplete. And then it waited. It waited for 33 years. No spacecraft visited Mercury between 1975 and 2008. 33 years during which the planetary science community worked with the Mariner 10 data, analyzing and reanalyzing the images, refining models of the surface geology and interior structure, debating the implications of the magnetic field, gradually building a more sophisticated understanding of what the available data meant. Proposals for follow-up Mercury missions were made and studied, and for various reasons, the extraordinary difficulty of reaching Mercury with the orbital insertion fuel required to actually enter orbit rather than just fly past, repeatedly deferred or canceled. Getting to Mercury is harder than it sounds. The planet is not simply close. It is close and moving fast, deep in the sun's gravitational well, in an orbit that requires any spacecraft coming from Earth to slow down enormously to match Mercury's orbital velocity rather than simply falling toward the sun. The delta V, the change in velocity required to enter Mercury orbit, is comparable to reaching the outer solar system. Getting to Mercury efficiently requires either enormous fuel loads or complex multi-year trajectories using multiple gravitational assists. It was this trajectory challenge that made Mercury exploration so difficult for so long, and that made the mission that eventually succeeded, Messenger, one of the more remarkable engineering achievements in the history of planetary exploration. The second act was Messenger. Messenger, an acronym standing for Mercury Surface, Space Environment, Geochemistry and Ranging, launched on August 3, 2004 from Cape Canaveral. It did not travel directly to Mercury. It could not. The delta V required for a direct trajectory would have required more fuel than the spacecraft could carry. Instead, Messenger flew a trajectory of extraordinary complexity: one Earth flyby in August 2005, two Venus flybys in October 2006 and June 2007, and three Mercury flybys in January 2008, October 2008, and September 2009, each one using the gravity of the encountered planet to slow the spacecraft slightly, gradually adjusting its orbit until Mercury orbital insertion became achievable with the fuel remaining on board. 6.5 years of interplanetary travel, more than 15 orbits of the Sun, one Earth flyby, two Venus flybys, three Mercury flybys, all in service of slowing down enough to be captured by Mercury's gravity on March 18, 2011. When Messenger entered Mercury orbit, it became the first spacecraft in history to orbit the innermost planet. Mariner 10 had flown past 3 times in 3 years. Messenger would orbit Mercury for more than 4 years, completing more than 4,000 orbits, returning more than 100,000 images, and transforming the planet from a partially known world into one of the most thoroughly characterized bodies in the inner solar system. What Messenger found rewrote the textbook on Mercury. The previously unimaged hemisphere was revealed for the first time, a surface continuing the pattern of heavy cratering seen by Mariner 10, but with important differences and new features. The full extent of the Caloris Basin was mapped, its diameter confirmed at approximately 1,550 kilometers, its interior volcanic plains characterized, the chaotic antipodal terrain identified and studied. Thousands of lobate scarps, the compression features created by Mercury's long-term shrinkage, were cataloged, and their distribution across the global surface analyzed. The surface composition, measured by Messenger's X-ray and gamma-ray spectrometers, revealed something unexpected. Mercury's surface is rich in sulfur and poor in iron, a composition very different from what simple models of planetary formation would predict for the innermost, most metal-rich planet. The surface abundances suggested that Mercury's crust formed from materials quite different from anything found in Earth's crust, and that the mantle from which those materials were derived had a chemistry that remains incompletely understood. Dark material, a substance with very low reflectivity, found in certain surface features including hollows and deposits around some craters, turned out to be widespread and geologically significant. Its composition was not immediately apparent from Messenger's instruments, but its presence pointed to volatile-rich materials that had somehow survived on Mercury's surface despite the planet's extreme thermal environment. And the hollows, shallow, irregular depressions found on the floors and walls of some craters, with no clear analog on any other planetary body, turned out to be one of Mercury's most distinctive and mysterious surface features, their origin and composition, a subject of active research and debate. Messenger's mission ended on April 30, 2015, when the spacecraft exhausted its fuel and crashed into Mercury's surface, unable to prevent its orbit from decaying any further. It hit at approximately 3.91 kilometers per second, creating a new small crater on the planet it had spent 4 years studying, one final contribution to the geological record it had spent those years reading. By the time it crashed, Messenger had answered most of the major questions that Mariner 10 had raised. And in answering those questions, it had raised new ones about the composition of the dark material, about the origin of the hollows, about the mechanism of Mercury's offset magnetic field, about the detailed structure of the interior. The third act was already in progress before Messenger's mission ended. Colombo is a joint mission between the European Space Agency and the Japan Aerospace Exploration Agency, the most ambitious Mercury mission ever attempted, consisting not of one spacecraft but two, traveling together to Mercury before separating into distinct orbits to study the planet simultaneously from different perspectives. It launched on October 20, 2018, and its journey to Mercury is even more complex than Messenger's, involving 1 Earth flyby, 2 Venus flybys, and 6 Mercury flybys before orbital insertion, with arrival at Mercury planned for late 2026. The mission is currently in its cruise phase, gradually working its way toward the innermost planet through the gravitational mechanics of the inner solar system. Colombo carries instruments of greater sensitivity and broader capability than Messenger, designed specifically to address the questions that Messenger left open. Its dual spacecraft configuration will allow simultaneous measurements of Mercury's magnetic field from 2 locations, providing 3-dimensional information about the field's structure that a single spacecraft cannot deliver. Its spectrometers will characterize surface composition in greater detail. Its radio science instruments will constrain the interior structure more precisely than any previous mission. The third act of Mercury exploration is approaching its most productive phase. 3 missions, 40 years of spacecraft exploration. A planet that went from being a mostly unknown point of light to one of the most scientifically rich bodies in the inner solar system. And still, Mercury keeps its deepest secrets. The dark material covering portions of its surface, the hollows that appear to be actively forming even today, the magnetic field offset from the planet's center by 1/5 of its radius, the composition of the volatile-rich materials that seem to contradict simple models of the planet's formation in the hottest region of the early solar system. The missions changed everything we knew. They also revealed just how much there is still to know. Rest in the long journey of discovery, from a point of light above the horizon to a world of craters and ice and magnetic mysteries, revealed by 3 extraordinary spacecraft across 5 decades of exploration. The mysteries are still waiting, and next, we descend into the deepest of them. Mercury's greatest mysteries. Science does not end with discovery. It deepens. Every question answered in the history of planetary exploration has revealed beneath its resolution a layer of more specific, more nuanced, more challenging questions that the answer itself exposed. The discovery that Mercury had a magnetic field did not close a chapter, it opened one. The confirmation of polar ice did not satisfy scientific curiosity, it redirected it. The complete global mapping of Mercury's surface by Messenger did not produce a finished portrait of a fully understood world. It produced a catalog of things that require explanation and currently have none. Mercury, after 5 decades of spacecraft exploration, is better known than at any point in human history, and it is also, in certain specific and important ways, more mysterious than it was before we looked closely. This is not a failure of science, it is how science works. The closer you look, the more detail emerges, and the more detail emerges, the more questions present themselves. Mercury, examined at the resolution that Messenger provided, turns out to be a world whose surface and interior contain phenomena that the existing frameworks of planetary science do not fully explain. The mysteries are not vague, they are specific. They have names and locations and measurements attached to them, and they are waiting patiently for the instruments of BP Colombo and the scientists analyzing its data to either explain them or deepen them further. The first and perhaps most visually striking of Mercury's unsolved mysteries is the dark material. Mercury's surface is not uniformly bright. Different regions reflect different fractions of the sunlight that strikes them. Some areas are brighter, some darker, in ways that correspond to differences in surface composition, particle size, and the degree of space weathering the material has experienced. This kind of albedo variation is normal and expected on any rocky planetary surface. What is less normal, what caught the attention of messenger scientists as the global surface maps were assembled, is the nature of certain dark deposits found around specific geological features on Mercury's surface. Around some impact craters, in certain hollows, associated with volcanic features and pyroclastic deposits, there is material that is darker than the surrounding terrain in a way that is not explained by simple differences in silicate composition or space weathering effects. The dark material has been characterized spectroscopically, its reflectance properties measured across multiple wavelengths, and the results point toward carbon-bearing compounds as a likely constituent. Graphite pure carbon in a crystalline form has been proposed as a candidate, and some models suggest that Mercury's original crust may have been rich in graphite, formed from a carbon-saturated magma ocean early in the planet's history. If Mercury's primordial crust was graphitic, black, absorptive, visually dark, then the dark material now seen associated with certain impact features may be excavated ancient crust, brought to the surface by impacts that punched through the overlying volcanic plains and exposed the original graphitic basement beneath. This would make Mercury unique among the rocky planets, the only world known to have had a graphite crust as its original surface layer. A planet whose earliest face was not the pale silicate rock of other worlds, but a dark carbon material, subsequently buried under billions of years of volcanic resurfacing, and now re-exposed in patches wherever impacts have dug deeply enough to reach it. The hypothesis is compelling. It is not yet confirmed. The composition of the dark material remains an active area of investigation, and BP Colombo carries instruments better suited than messengers to characterize it definitively. The second mystery is the hollows. Nothing quite like Mercury's hollows has been found on any other planetary body in the solar system. They are shallow, irregular depressions, typically tens of meters to a few kilometers in diameter and tens of meters deep, found on the floors, walls, and central peaks of certain impact craters, as well as in some other geological settings. Their edges are sharp and irregular. Their floors are bright, significantly more reflective than the surrounding terrain, and they appear, from the freshness of their appearance and the absence of subsequent impact craters on their floors, to be geologically young, possibly forming today. This last point is what makes the hollows so scientifically intriguing. Mercury is generally considered a geologically quiet world, a planet whose active geological period ended billions of years ago, whose surface changes only through the slow accumulation of impact craters and the gradual compression wrinkles of a slowly shrinking interior. Geologically active features forming on Mercury's surface in the present day would be remarkable. The leading hypothesis for hollow formation involves the sublimation of volatile materials from Mercury's surface, the direct transition of certain compounds from solid to vapor without passing through a liquid phase, driven by the intense solar radiation and the harsh space environment. If Mercury's crust contains volatile compounds, sulfides, chlorides, or other materials that are unstable under the conditions at Mercury's surface, those materials could be gradually lost from the surface in the most highly irradiated environments, leaving behind the shallow depressions and bright residual material that characterize the hollows. This would make the hollows evidence of ongoing geological change, a surface that is still being actively modified, not by internal heat and volcanism, as in the planet's youth, but by the solar environment stripping volatile material from the exposed crust. What volatile compounds are involved, and why they are present on Mercury's surface in the first place, given the planet's formation in the hottest region of the early solar system, remains uncertain. The composition of the hollow floors is one of the primary scientific targets for BP Colombo's surface chemistry instruments. The third mystery is the one we touched on in our section on Mercury's iron heart, the magnetic field offset. Mercury has a magnetic field, That alone remains remarkable for a planet of Mercury's size and age. But the specific character of that field, the fact that its dipole axis is offset northward from the planet's center by approximately 480 kilometers, presents a problem that current theories of planetary magnetic field generation cannot fully explain. In standard dynamo theory, the magnetic field produced by convecting liquid metal in a planetary core should be roughly centered on the planet. The symmetry of the convection patterns should produce a roughly symmetric field. Small offsets can arise from asymmetries in the core, but an offset of 480 kilometers, representing nearly 20% of Mercury's total radius, is not a small deviation. It is a structural feature of the field that requires explanation. Several hypotheses have been proposed. One involves a stably stratified layer at the top of the liquid outer core, a region where the core fluid is not actively convecting, but is instead in a stable density stratification that modifies the magnetic field generated by the convecting region beneath it. This stratified layer, in some models, can filter the magnetic field in ways that amplify the offset of the observed dipole. Another hypothesis involves the specific geometry of the solid inner core, its size, shape, and the details of how solidification is occurring at the inner core boundary. Asymmetric growth of the inner core could drive asymmetric convection patterns in the outer core, producing an asymmetric field. None of these hypotheses has been definitively confirmed. Bepi Colombo's dual spacecraft configuration, allowing simultaneous magnetic field measurements from two different orbital positions, is specifically designed to provide the three-dimensional field characterization needed to test these models. The offset field is perhaps the single most important unresolved question about Mercury's interior, and its resolution may require revising fundamental aspects of how planetary dynamos are understood to operate. The fourth mystery concerns Mercury's composition, specifically the abundance of volatile elements on its surface. Mercury formed in the hottest region of the protoplanetary disk, where volatile compounds should have been unable to survive in solid form. The planet formed from exclusively refractory materials. The high melting point metals and silicates that could condense close to the young sun should have a volatile pore composition. Its surface should be largely free of the sulfur, chlorine, sodium, potassium, and other volatile or moderately volatile elements that are found in abundance in the outer solar system. Messenger's surface chemistry measurements told a completely different story. Mercury's surface is rich in sulfur, far richer than Earth's surface, far richer than what any simple model of Mercury's formation would predict. It contains measurable amounts of chlorine. Its surface sodium abundance is higher than expected. The abundances of moderately volatile elements are, by the standards of what simple models predicted, startlingly high. This compositional surprise remains one of the most challenging problems in Mercury science. How did a planet formed so close to the Sun, in conditions so hot that volatiles should have been driven off before they could be incorporated into solid material, end up with a volatile-rich surface composition? Several possibilities have been proposed. Perhaps Mercury formed farther from the Sun and migrated to its current position after acquiring its volatile-rich composition. Perhaps the giant impact that may have stripped Mercury's mantle changed the planet's surface composition in ways not yet fully modeled. Perhaps the delivery of volatile-rich material by comets and asteroids after Mercury's formation contributed more to the surface composition than simple accretion models suggest. None of these explanations is fully satisfactory. Mercury's surface composition remains, in the words of several planetary scientists, a first-order unsolved problem in inner solar system science. The fifth mystery is perhaps the most fundamental of all. Mercury is shrinking. We established this in our section on the Iron Heart, the long-term cooling of the interior causing the planet to contract, the surface crust buckling into the lobate scarps that record this compression. Messenger's global mapping allowed a comprehensive inventory of these scarps, and the total surface area reduction implied by their distribution was calculated. The answer was approximately 5 to 7 kilometers of radius reduction over Mercury's history. But when this contraction was compared to the predictions of thermal evolution models, calculations of how much a planet of Mercury's size and composition should have contracted as it cooled over 4.6 billion years, the observed contraction was significantly smaller than predicted. The models said Mercury should have shrunk more than the surface evidence suggests. This discrepancy between the predicted amount of shrinkage and the observed amount points to something in Mercury's thermal evolution that the models are not capturing. Perhaps the interior has not cooled as much as simple models predict, consistent with the persistence of the liquid outer core. Perhaps the core composition produces a different volumetric change upon cooling than assumed. Perhaps the early thermal history of the planet was different from what current models describe. The shrinkage discrepancy is a clue. It is pointing at something real about Mercury's interior that the current generation of models is missing. What that something is remains an open question. Taken together, these mysteries, the dark material, the hollows, the offset magnetic field, the volatile-rich composition, the shrinkage discrepancy, paint a portrait of Mercury as a world that has resisted simple understanding. Each mystery is connected to the others in ways that are not yet fully apparent. The volatile-rich surface composition may be related to the formation of the hollows. The dark material may be related to the carbon content of the original crust. The offset magnetic field may reflect the same interior structure that explains the shrinkage discrepancy. Or the connections may be different from what current models suggest, or there may be connections that no one has yet identified. This is the frontier of Mercury science, the edge where confirmed knowledge gives way to active investigation, where the data from existing missions has been analyzed and the questions have been sharpened, and where the next generation of measurements is already on its way. Bepi Colombo is approaching, its arrival is coming, and Mercury's deepest secrets are waiting. Let those mysteries settle quietly around you, the dark surface and the strange hollows in the offset field and the volatile-rich rock of the closest planet to the Sun. The questions are real, and the answers are coming. And in our next passage, we ask the most human question of all: could we ever go there ourselves? Could humans ever visit Mercury? There is a particular kind of question that human beings have always asked about distant and difficult places. Not the scientific questions, not the questions about composition or magnetic fields or thermal evolution or the origin of mysterious surface features. Those are the questions that spacecraft answer, that instruments measure, that data constrains and models explain. They are important questions. They are the questions that have driven 5 decades of Mercury exploration. But alongside those questions, quieter and more personal, there is always the human one. Could we go there? Not a robot, not an instrument package wrapped in thermal shielding and solar panels and launched on a years-long trajectory. A human being, warm, fragile, biological, carrying the same basic physiology that evolved on the plains of Africa under a sun 90 degrees of latitude from the equator on a planet with a thick, protective atmosphere. Could such a creature travel to the closest planet to the Sun, survive its thermal extremes and radiation environment, and return home? The honest answer, in the current state of human technology, is no. Not no in the sense of a fundamental physical impossibility. There is nothing in the laws of physics that categorically prevents a human being from visiting Mercury. But no in the sense that the practical challenges are so severe, so numerous, and so far beyond the capabilities of any technology currently existing or in near-term development, that the question belongs more to the domain of very long-term futures than to any planning horizon recognizable from the present. Let us understand why. The first and most immediately obvious challenge is the journey itself. Getting to Mercury is, as we explored in our previous section, extraordinarily difficult even for robotic spacecraft. The combination of Mercury's deep position in the Sun's gravitational well and its high orbital velocity means that any spacecraft traveling from Earth must either carry enormous quantities of fuel to decelerate into orbit or fly a complex multi-year trajectory using gravitational assists from other planets. Messenger took 6.5 years to reach Mercury orbit, but Colombo, currently en route, will have traveled for approximately 8 years by the time it arrives. These timescales are already challenging for robotic missions. The spacecraft must function reliably for years in the interplanetary environment before their primary science objectives can begin. For a crewed mission, 6 to 8 years of interplanetary travel is not merely challenging. It is, with current life support technology, essentially impossible. No life support system currently exists that could sustain a human crew for 6 years in a spacecraft with the mass constraints of an interplanetary mission. No food production system has been demonstrated at the required scale and reliability. no radiation shielding sufficient for years of interplanetary exposure has been built and tested. And those problems apply before the spacecraft even arrives at Mercury. They apply to the journey alone. Faster trajectories to Mercury are theoretically possible. A more direct trajectory, one that does not use multiple gravitational assists, but instead applies propulsive thrust to decelerate more rapidly, could reduce the transit time to Mercury to perhaps 3 to 4 months. This is comparable to the journey time to Mars, which is currently being planned for crewed missions within the coming decades. But this faster trajectory comes at an enormous cost in fuel. The delta-V required for a fast crewed transit to Mercury is significantly greater than for a Mars mission, greater, in fact, than for most destinations in the outer solar system. The massive propellant required to execute such a trajectory and then decelerate into Mercury orbit, using rocket propulsion currently available or in near-term development, would be staggering. Not merely large, staggering. The kind of mass that exceeds any launch capability that exists today or is planned for the near future. Advanced propulsion systems, nuclear thermal rockets, nuclear electric propulsion, or more speculative technologies could change this calculation. A nuclear thermal rocket, for example, delivers significantly higher specific impulse than chemical rockets, requiring less propellant mass to achieve the same delta-V. If such systems are developed, demonstrated, and made safe for crewed use, they would substantially reduce the fuel mass required for a fast Mercury transit. But nuclear thermal propulsion for crewed spaceflight, while technically feasible in principle and studied extensively, has not been demonstrated in flight. It remains a technology of the future, a potentially near future, but the future nonetheless. Assume, for the purposes of exploring the question, that the transit time and propulsion challenges can be solved. A crewed spacecraft arrives at Mercury in 3 months, enters orbit, and prepares to land a crew on the surface. The challenges that then present themselves are of a different character, not engineering challenges of fuel and trajectory, but environmental challenges posed by Mercury itself. The first is thermal. Mercury's dayside surface reaches 430 degrees Celsius. No spacesuit currently designed for human planetary surface operations can protect an astronaut in those conditions. The spacesuits used for Apollo lunar operations were designed for a surface that reached approximately 127 degrees Celsius, already hot by terrestrial standards, but manageable with appropriate thermal control systems. A suit capable of rejecting the heat load of Mercury's dayside environment would need thermal control systems far beyond anything developed for lunar or Mars operations. The solution would likely involve operating exclusively on the night side, in the polar regions, or in the permanently shadowed craters, the same locations where ice deposits are found. These are the only regions of Mercury's surface where temperatures are within ranges that any conceivable near-future spacesuit could manage. The permanently shadowed craters, with their temperatures of -170 to -200 degrees Celsius, present the opposite thermal challenge, extreme cold rather than extreme heat. But extreme cold, while difficult, is a more tractable engineering problem than extreme heat for a suited astronaut, because generating heat is energetically easier than rejecting it. A crewed Mercury surface mission would therefore almost certainly focus on the polar regions, and specifically on the polar shadowed craters, where the thermal environment is manageable, where water ice provides a local resource, and where the science of Mercury's volatile inventory is most directly accessible. The second environmental challenge is radiation. Mercury's weak magnetic field provides minimal protection against solar energetic particles and cosmic rays. The planet's lack of atmosphere means there is no atmospheric shielding. Any human being on Mercury's surface is exposed to the full radiation environment of interplanetary space, augmented by the increased solar radiation intensity at Mercury's distance from the Sun. Solar energetic particle events, solar storms, are a particular concern. At Earth, the magnetosphere and atmosphere together provide substantial protection during even major solar storms. At Mercury, an astronaut caught on the surface during a major solar energetic particle event would receive a radiation dose that could cause acute radiation syndrome, radiation sickness, and would significantly increase lifetime cancer risk. Managing this radiation environment would require either extensive shielded habitat structures on the surface, providing a radiation refuge that astronauts could reach quickly when solar storm warnings were issued, or operational protocols that limited surface exposure during periods of elevated solar activity. The Sun, from Mercury's surface, is not just visually overwhelming. It is actively dangerous in ways that the Sun at Earth's distance is not. The third challenge is communication and mission support. Mercury, being the closest planet to the Sun, is not always close to Earth. When Mercury is on the far side of the Sun from Earth, communication between the planet and Earth requires signals that pass near the Sun, where the solar corona introduces signal delays and distortions that can make reliable communication difficult or impossible. Periods of solar conjunction, when Mercury is directly behind the Sun as seen from Earth, would produce communication blackouts lasting days to weeks. A crewed mission to Mercury would need to be designed to operate autonomously through these blackout periods, making decisions without real-time communication with Earth, responding to emergencies without the ability to consult ground controllers, managing systems with no possibility of immediate outside support. This is a challenge for any crewed deep space mission, but Mercury's proximity to the Sun means that communication geometry is more frequently problematic than for missions to Mars or other destinations where solar conjunction is a periodic event rather than a recurring operational condition. There is one scenario in which human presence at Mercury becomes considerably more conceivable, and it does not involve landing on the surface at all. A crewed Mercury orbiting mission, analogous to the Apollo 8 mission that orbited the Moon without landing, would avoid the surface thermal and radiation challenges, while still allowing human scientists in close proximity to Mercury to conduct observations, deploy surface probes, and interact with robotic systems on the surface in near real time, rather than with the significant communication delays that limit remote robotic operations from Earth. From Mercury orbit, humans could direct robotic systems on the surface, responding to what those systems find with a speed and flexibility that Earth-based operators cannot match. The scientific return of a crewed orbital mission might approach or exceed that of a crewed landing mission, at significantly lower technological and operational risk. Such a mission remains far beyond current capabilities. The transit challenges apply equally to an orbital mission as to a landing mission, but it represents a potential intermediate step on any longer-term path toward human presence at Mercury. The most speculative long-term scenario for human presence at Mercury involves the polar regions and the ice deposits. The permanently shadowed craters near Mercury's poles offer a combination of features that make them the only plausible locations for long-term human habitation on the planet. Manageable temperatures, water ice as a local resource, access to sunlight on nearby crater rims for solar power generation, sufficient distance from the equatorial dayside to avoid the worst thermal environment. A polar habitat buried under regolith for radiation shielding, powered by solar panels on permanently sunlit ridge crests, supplied with water from the ice deposits in the craters below, is technically conceivable in the same general way that a lunar polar habitat is conceivable. The challenges are greater in every dimension: more radiation, more difficult thermal management, more complex logistics, more demanding transit requirements, but the basic concept is not physically impossible. Whether the scientific and strategic value of a Mercury surface presence would justify the extraordinary technological development required to make it possible is a question that depends entirely on how ambitious humanity's long-term space program turns out to be, and how much the exploration of the innermost planet is valued relative to other destinations that are more accessible. The Moon is closer, Mars is more habitable in relative terms. The asteroid belt offers resources more accessible than Mercury's surface. Any realistic near-term human space program will prioritize those destinations. Mercury, if humans ever reach it, will be a destination of the far future, a world visited after the more accessible destinations of the inner solar system have been established as bases for deeper exploration. But the question of whether we can go there is ultimately less interesting than the question of what we would find if we did. The mysteries we explored in our last section, the dark material, the hollows, the offset magnetic field, the volatile rich composition, are questions that spacecraft can approach, but that human scientists on the surface could engage with in ways no robot can fully replicate. The ability to pick up a rock and examine it, to notice something unexpected and immediately change the plan, to bring the full pattern recognition capacity of a human mind trained in geology to bear on a landscape in real time. Mercury has things to show us that our best instruments may not be equipped to notice. And somewhere in the long future of human exploration, in the era after the Moon and Mars and the asteroid belt have been settled, after propulsion systems have been developed that make the inner solar system accessible on timescales compatible with human life, someone will go. They will stand in a permanently shadowed crater near Mercury's south pole, suited against the cold, surrounded by ice that has been sitting in the dark since before the first cell divided on Earth. They will look up and see, above the crater rim, the blazing black sky of the closest world to the sun itself enormous and overwhelming, filling more of the sky than any human eye has ever seen it fill before. And they will understand, in a way that no amount of data or imagery or scientific analysis can fully convey, what it means to stand on the innermost world. Let that distant future rest gently in your mind. Humans may one day stand on Mercury, in the cold and the shadow, beneath the enormous sun. And in our next passage, we follow the very longest thread of all, to the final chapter of Mercury's story. Mercury's future. Every story told by planetary science eventually arrives at the same place. Not because planetary scientists are pessimistic, or because the universe is unkind, or because the arc of cosmic history bends inevitably toward darkness, but because stars are not eternal, and the planets that orbit them share their fate, and the solar system we inhabit is not a permanent arrangement, but a temporary one extraordinarily long-lived by any human measure, but finite by the standards of deep time. We have stood at this threshold before, in our documentaries about Earth and the Moon, looking far into the future, past the comfortable familiarity of the present, past the timescales of human civilization and biological evolution and geological change, into the era when the sun itself begins its final transformation and the inner solar system becomes something unrecognizable. Mercury, being the innermost planet, closest to the sun, smallest and most geologically quiet, arrives at that final transformation before any of the others. Its story ends first. But the ending is not simple, and the path to it passes through changes that are already underway, slow, patient, largely invisible on human timescales, but real and measurable and irreversible. Begin with what is happening to Mercury right now. The planet is shrinking. We established this in our section on the Iron Heart, the gradual cooling and contraction of the interior, recorded in the lobate scarps that buckle across the surface as the crust accommodates the decreasing volume beneath it. This process is ongoing. Messenger's data confirm that some of the youngest scarps on Mercury's surface are geologically recent, suggesting that the planet's contraction has continued into the relatively recent past and has not yet ceased. Over the next billion years, this contraction will continue. Mercury's core will cool further slowly, given the volatile-rich composition that has kept it partly liquid far longer than simple models predict, but inevitably. As the core cools, more of the liquid iron will solidify, shrinking in volume as it does so. New scarps will form, old ones will be modified. The surface will continue to be reshaped, not by volcanism or tectonics in the dynamic sense that Earth's surface is reshaped, but by the slow, compressional force of a planet that is still adjusting to the thermal legacy of its formation. At some point, the liquid outer core will fully solidify. When that happens, when the last flowing iron in Mercury's interior freezes, the dynamo that generates the magnetic field will cease. Mercury will lose its magnetic field entirely, as Mars lost its own billions of years ago when its smaller core cooled and solidified. The timing of this event is uncertain. Mercury's core has already survived far longer in a partially liquid state than simple models predicted, and the precise timeline for complete solidification depends on the composition and thermal conductivity of the core materials in ways that are not yet fully characterized. It could happen in hundreds of millions of years. It could take longer, but it will happen. When it does, Mercury's magnetic field will join its volcanism as a feature of the past, another chapter of geological activity that ran for billions of years and then quietly ended. The loss of the magnetic field will change Mercury's surface environment in ways that are already not dramatically different from the present, but will become subtler and more cumulative over geological time. Mercury's current magnetic field, weak as it is, provides some minimal interaction with the solar wind, creating a small magnetosphere that deflects some fraction of the charged particle flux before it reaches the surface. The effects of this minimal shielding are modest. Mercury's surface is already heavily bombarded by solar wind particles and cosmic rays, and the protection offered by the weak field is far less than what Earth's robust magnetosphere provides, but it is not zero. When the field disappears, the full solar wind will interact directly with Mercury's exosphere, the tenuous near vacuum that currently constitutes the planet's atmospheric presence. The rate at which solar wind particles sputter material from Mercury's surface will increase slightly. The exosphere itself, maintained partly by solar wind interactions with the surface, will be modified. Over geological timescales, this increased exposure may gradually alter the composition of Mercury's surface in the polar regions, affecting the stability of the ice deposits. The dynamics of the polar cold traps depend partly on the electromagnetic environment, on how solar wind particles interact with the surface and exosphere near the poles. Without any magnetic field to structure that interaction even minimally, the polar environment will change. Whether the ice deposits will be significantly depleted by this change, or whether the geometry of the permanently shadowed craters will continue to protect them regardless of the electromagnetic environment, is a question current models have not fully resolved. While Mercury's interior is slowly dying, the external environment that defines the planet's existence is slowly changing. The Sun, as we have explored in previous documentaries, is gradually brightening. Over the past 4.6 billion years, solar luminosity has increased by approximately 30%. It will continue to increase slowly, but relentlessly, as hydrogen in the core is consumed and the Sun's structure gradually adjusts. For Earth, this brightening represents a long-term challenge, eventually, over hundreds of millions to billions of years, leading to the loss of the oceans and the end of the conditions that support life. For Mercury, which already receives 4.5 to 10 times more solar radiation per square meter than Earth, the consequences of a brightening sun are different in character, but no less significant. As solar luminosity increases over the next billion years, the average temperature on Mercury's dayside will rise. Not dramatically in the near term, a 10% increase in solar luminosity increases the equilibrium temperature of an airless body by only a few percent in absolute temperature. But cumulatively, over hundreds of millions to billions of years, the dayside surface will grow hotter than it is today. This increasing heat load will gradually change the thermal environment of the polar cold traps. As solar radiation intensity increases, the thermal shadows cast by crater rims will become warmer, not from direct illumination, but from the increased infrared radiation emitted by the sunlit surfaces surrounding the shadowed regions. The temperature in permanently shadowed craters will rise, not to the dayside values. The permanent shadow will still be cold, but away from the minus 200 degrees Celsius temperatures that currently preserve the ice so effectively. At some point in the far future, the temperatures in the polar cold traps may rise above the threshold where water ice remains stable indefinitely. The ice will begin to slowly sublimate. The ancient deposits, preserved for billions of years in the cold and dark, will gradually diminish. The polar ice of Mercury, one of the most surprising and scientifically significant discoveries in the history of planetary exploration, is not permanent. It has a future as surely as it has a past, and that future ends in the gradual loss of water molecules to space as the solar environment intensifies. The most dramatic phase of Mercury's future arrives with the Sun's red giant phase. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core and begin its transition to a red giant, expanding enormously, its luminosity increasing by factors of hundreds to thousands, its outer atmosphere swelling outward through the inner solar system. Mercury, as the innermost planet, will be the first to meet this expanding stellar atmosphere. The timeline of what happens to Mercury during the Sun's red giant expansion depends on the details of the expansion, how rapidly the Sun grows, how much mass it loses through its stellar wind as it expands, and how that mass loss affects the orbits of the inner planets. As a star loses mass, its gravitational pull weakens, and the orbits of its planets expand in response, a planet's orbital radius increasing proportionally to the Sun's mass loss. This orbital expansion provides a small reprieve for the inner planets. If the Sun loses sufficient mass during its ascent to the red giant phase, Mercury's orbit will expand outward, moving the planet away from the encroaching stellar atmosphere. But current stellar evolution models suggest that this orbital expansion is unlikely to save Mercury. The Sun's radius during its red giant peak is expected to reach somewhere between 100 and 200 times its current size. Mercury's current orbit takes it no closer to the Sun than 46 million kilometers, approximately 0.31 astronomical units. Even accounting for orbital expansion due to solar mass loss, Mercury's orbit is expected to remain well within the Sun's red giant radius. Mercury will be engulfed. The engulfment of Mercury by the expanding Sun is not a dramatic explosion or a collision in any ordinary sense. It is an immersion, the planet's orbit gradually being swept within the expanding outer atmosphere of the red giant, Mercury moving through a medium of tenuous but extremely hot and extensive stellar gas rather than through the near vacuum of interplanetary space. As Mercury orbits within the stellar atmosphere, drag forces will slow it. As it slows, its orbit will decay, spiraling inward toward lower and lower orbits, moving ever deeper into the stellar atmosphere. The process is self-reinforcing. Deeper immersion means greater drag, means faster orbital decay, means still deeper immersion. The surface of Mercury, already scorched by billions of years of intense solar radiation, will experience temperatures that dwarf anything in its previous history. Not 430 degrees Celsius, not hundreds of degrees Celsius, thousands of degrees, the temperature of the stellar atmosphere itself, enveloping the planet as it spirals inward. The crust will melt, the mantle will vaporize. The iron core, the dominant feature of a planet that has been mostly core for its entire existence, will endure longest dense iron holding together under conditions that destroy the surrounding silicate layers. But ultimately the core too will be destroyed, its material absorbed into the stellar atmosphere, contributing its iron and nickel to the composition of the expanding giant star. Mercury will cease to exist as a distinct body. Its matter will become part of the Sun that made it, returned, after 9 to 10 billion years of separate existence as a planet, to the stellar material from which it ultimately originated. The smallest planet, the fastest orbiting, the most core-dominated, the most thermally extreme, Mercury in the end, falls back into the fire. After the red giant phase, the Sun will shed its outer layers in a planetary nebula, a shell of expanding gas lit by the hot remnant core left behind. The white dwarf that remains will cool over billions of years, radiating the last of its heat into the cold of space. In the debris of what was once the solar system, traces of Mercury's material will persist. Iron and nickel and silicate minerals, now dispersed through the stellar wind, perhaps incorporated into new dust clouds, perhaps eventually gathered by gravity into new planetary systems, orbiting new stars in the distant future of the galaxy. The atoms of Mercury, the iron of its enormous core, the carbon of its dark surface material, the water ice of its polar deposits will not be destroyed. They cannot be. Matter persists. What was Mercury will become something else, part of a stellar atmosphere, part of a planetary nebula, eventually part of whatever comes next in the long story of that corner of the galaxy. The planet ends, the matter continues. Let the long future of the innermost planet settle quietly into sleep, the cooling core and the rising sun and the final, patient return to the fire. And in our last passage, we step back to the widest view of all and ask what Mercury, in all its strangeness, means. Why Mercury is one of the most extraordinary worlds. Step back one more time. Not from this room or this night, or this moment of quiet at the end of a long journey through the story of the smallest and closest planet. Step back from the entire framework of comparison that shapes how most people think about the solar system, the tendency to rank planets by size or beauty or apparent complexity, to gravitate toward the dramatic rings of Saturn or the swirling storms of Jupiter or the romantic redness of Mars, and to leave Mercury somewhere near the bottom of the list. Too small, too close to the Sun, too cratered and too simple and too difficult to observe. Step back from all of that and look at Mercury for what it actually is. Not what it appears to be from the Earth's surface, a difficult and elusive point of light near the horizon. Not what it looks like in a simple catalog of planetary facts, smallest planet, fastest orbit, extreme temperatures, iron core. But what it actually is, in the full depth and complexity of everything we have explored together over the past 11 sections of this journey. A world of genuinely extraordinary character, a planet that has been surprising scientists since the moment we first visited it, and that continues to surprise them still. A body whose existence raises questions that touch the foundations of planetary science, and whose answers, when they finally come, will reshape how we understand the formation and evolution of rocky worlds throughout the universe. Consider what Mercury is, assembled from everything we now know. It is a planet that formed in the most extreme thermal environment of the early solar system, built from materials so refractory that most of the lighter compounds that make up the other rocky planets simply could not survive in solid form at Mercury's orbital distance. And yet, in direct contradiction to this origin, it has a surface rich in volatile elements that should never have been present in the first place. That contradiction alone is extraordinary. A planet whose formation conditions preclude volatile elements, but whose surface is measurably enriched in them. Every explanation proposed for this discrepancy requires either a dramatic revision of where and how Mercury formed, or a dramatic event, a giant impact, or early solar erosion that fundamentally changed the planet's composition after formation. In either case, Mercury's composition tells a story about the early solar system that is more complex and more dynamic than the simplest models suggest. This is not a minor anomaly. It is a first-order problem in inner solar system science, and its resolution will have implications not just for Mercury, but for understanding how rocky planets form around other stars throughout the galaxy. Mercury's interior is equally remarkable. The largest core fraction of any planet in the solar system, an iron heart that makes up perhaps 80% of the planet's mass, a ratio so extreme that it required either formation from uniquely metal-rich material or a catastrophic stripping of the mantle, or both. A core that has remained partially liquid far longer than any simple thermal evolution model predicted, kept fluid by a composition whose details are still being worked out. A magnetic field generated by that liquid core, weak, offset from the planet's center by nearly 20% of its radius, and unlike any other planetary magnetic field in the solar system in its specific character. A small planet that should have cooled and gone dark billions of years ago, but has not. A magnetic field that should not exist in a body of Mercury's size and age, but does. An interior whose behavior at every level of examination has defied the expectations of planetary scientists who first approached it with models calibrated on Earth. Mercury is not simple. It is perhaps the most structurally unusual planet in the solar system, precisely because it exists in an unusual place and formed under unusual conditions, and has evolved in ways that no simple extrapolation from other planets could have predicted. The surface is its own catalog of the unexpected. A planet simultaneously bearing the marks of the solar system's most ancient and violent history, the late heavy bombardment written in craters so old that their floors have been partially flooded by volcanic material that is itself billions of years old, and the marks of ongoing geological processes that are still active today. The hollows forming on timescales that may be geologically recent point to a surface that is not simply a dead archive of ancient events, but an active environment still being shaped by the interaction between Mercury's crust and the intense solar environment. The lobate scarps wrapping across the surface in long sinuous arcs, recording the ongoing contraction of a planet that is still slowly shrinking, still adjusting to the thermal history of its formation and evolution. The dark material, possibly the exposed remnant of Mercury's original graphite crust, a primordial black surface buried under billions of years of volcanic resurfacing, and now re-exposed by impacts that punch through to the ancient basement below. And in the polar regions, in the floors of permanently shadowed craters, water, ice, and organic compounds preserved in the cold and dark since before the first living cell appeared on Earth. Ice on the closest planet to the Sun. Organic material sitting in shadows that have not seen light since the solar system was young. Every layer of Mercury's surface, examined at sufficient resolution, reveals something that was not expected and is not yet fully explained. There is a perspective on Mercury that only becomes available when you consider it not as a planet in isolation, but as a member of a class, a representative of the rocky, differentiated, iron-cored bodies that populate the inner regions of planetary systems throughout the galaxy. We know from the exoplanet surveys of the past 3 decades that rocky planets are common. The Milky Way alone may contain tens of billions of rocky planets, many of those planets will be in the inner regions of their star systems, at distances analogous to Mercury's, orbiting stars not unlike the Sun. Many will have formed under conditions similar to those that shaped Mercury, in the hot inner disk, from refractory-rich material, in the intense radiation environment of a young star. Mercury is our only example of such a planet, the only object we can examine in detail that represents the class of hot, inner, iron-rich rocky worlds that may be among the most common types of planetary body in the galaxy. Whatever we learn about Mercury's formation, its interior structure, its magnetic field, its surface composition, its long-term thermal evolution, all of it has implications that extend far beyond this one small, fast-moving planet orbiting our own sun. Mercury is not just a planet. It is a sample, a nearby example of a planetary type that may exist in enormous numbers throughout the universe, and that we have no other way of studying at close range. In this sense, understanding Mercury is not a narrow scientific specialty. It is a contribution to the fundamental question of how rocky worlds form and evolve, a question relevant to the search for habitable environments, for conditions suitable for life, for understanding the cosmic context in which biology either arises or fails to arise. Mercury tells us something about where we might look and what we might find in the planetary systems of other stars. And then there is the human dimension of Mercury's story, the dimension that does not fit neatly into scientific categories, but is no less real for that. Mercury has been watched by human eyes for the entirety of recorded history. Every civilization that developed astronomical knowledge included Mercury in its observations, tracking its rapid movement across the sky, naming it after messenger gods and swift deities, weaving it into mythological systems and calendars and astrological traditions that stretched across thousands of years of human culture. For all of that time, we were watching a point of light. We were building elaborate frameworks of meaning around an object we could not see clearly, whose surface we had never imaged, whose interior we knew nothing about. And then in the span of a single human lifetime, from 1974 to the present, we sent 3 missions to Mercury, mapped its entire surface, characterized its magnetic field, confirmed the presence of polar ice, discovered the hollow formations in the dark material and the offset dipole and the volatile-rich composition. We went from a point of light to a fully mapped, scientifically characterized world of extraordinary complexity in about 50 years. 50 years, in the context of the thousands of years Mercury has been observed, this is a fraction of a moment. In the context of Mercury's 4.6 billion year history, it is essentially instantaneous. And yet in that fraction of a moment, that instantaneous burst of scientific attention, we learned more about Mercury than all the preceding generations of human beings combined. That is the power of the spacecraft age. That is what happens when human curiosity is equipped with the tools to actually reach the places it has long been contemplating. Bepi Colombo is on its way. Right now, as you rest, the joint European-Japanese spacecraft is moving through the inner solar system on its complex trajectory toward Mercury orbital insertion in 2026. It carries instruments designed specifically to address the questions that previous missions raised and left open. Its dual spacecraft configuration will provide a 3-dimensional view of Mercury's magnetic field for the first time. Its surface chemistry instruments will characterize the dark material and the hollow floors in greater detail than MESSENGER could achieve. Its radio science investigations will constrain Mercury's interior structure more precisely than any previous measurement. The next chapter of Mercury science is already written, not yet read, but already in progress. The data that Bepi Colombo will return will almost certainly answer some of the questions we have explored in this documentary, and it will almost certainly raise new ones. That is the nature of Mercury. The closer you look, the more there is to see. Take one final moment, here at the end of our journey, to hold Mercury in mind as a whole. The smallest planet, the fastest orbit, the most core-dominated structure, the most thermally extreme surface environment in the inner solar system, a magnetic field that should not exist but does, polar ice that should not survive but has, a surface that remembers 4 billion years of solar system history without erosion, without weathering, without the patient erasure that makes Earth's own ancient history so difficult to read. A world that, for most of human history, was known only as an elusive point of light near the sun, and that, in the space age, has revealed itself to be one of the most scientifically rich and structurally unusual bodies in the solar system. A planet full of contradictions and anomalies and unsolved mysteries, each one pointing at something real about the physics of planetary formation and evolution that we have not yet fully captured in our models. Mercury is not the most visually spectacular planet. It is not the largest or the most atmospherically dramatic or the most immediately inviting to human imagination. But it is extraordinary in the deepest sense, extraordinary in what it tells us about how rocky worlds form, how they evolve, how they fail to behave as simple models predict, and what the universe does with small iron-rich bodies that end up too close to the star that made them. It races around the sun in 88 days, as it has for 4.6 billion years. It will continue racing, growing slowly colder inside, its surface preserving its ancient record, its polar ice sitting patient in the permanent shadow, its magnetic field maintaining its improbable existence, until the sun itself comes to claim it. And in the time remaining, there is still much to learn. The messenger planet has more messages to deliver. Rest now, the smallest world orbits faithfully in the darkness, fast and ancient and full of secrets, closer to the fire than anything else in the solar system, and remarkable in ways that no catalog of basic facts could ever fully convey.